Buenas tardes a todas. Empezamos la sesión de hoy. La verdad es que tenemos un programa fantástico, muy centrado en biomarcadores. En primer lugar, vamos a tener a Dani Alcolea, que nos va a hablar del presente, que son los marcadores de líquido cefalorraquídeo. Luego vamos a tener a Marc Suárez, que nos va a hablar de lo que nos viene, que son los marcadores de sangre, los marcadores de plasma. Y para acabar vamos a tener a Rik Ossenkoppele, que nos va a hablar del PET, que también es presente, pero también es futuro, ¿no? Y comenzamos con Dani Alcolea. Dani Alcolea es neurólogo clínico del Hospital Sant Pau, de la unidad de memoria del Hospital Sant Pau. Es amigo y colaborador desde hace tiempo de nuestro grupo de Santander y es uno de los principales expertos en este campo, en el campo de los marcadores del líquido cefalorraquídeo, y estamos muy agradecidos y yo creo que vamos a disfrutar de una charla fantástica. Muchas gracias, Dani, cuando quieras.
Bueno, muchas gracias, Pascual, por la invitación y por la presentación. Mi presentación de hoy es básicamente, voy a hablar de marcadores en líquido cefalorraquídeo. Sí que me centraré obviamente en el presente, porque creo que es lo que tenemos a día de hoy disponible para hacer el diagnóstico. Pero también mencionaré brevemente el pasado, de dónde venimos, y también algunos apuntes sobre el futuro y sobre dónde creo que puede estar el papel de estos marcadores de líquido cuando se implementen los marcadores de plasma que, como ha comentado Pascual, están al caer, ¿no? Pues bien, estos son mis conflictos de interés. Yo soy neurólogo clínico, pero sí que es verdad que he tenido especial interés en los marcadores de líquido desde que empecé la carrera de investigación y básicamente han sido el foco de mi tesis doctoral y luego de mis líneas de investigación, ¿no? Si hablamos brevemente del pasado, la realidad es que el líquido cefalorraquídeo se ha utilizado para el diagnóstico de enfermedades neurológicas desde hace siglos, ¿no? Y ya de hecho en el siglo XVII Thomas Willis describía alteraciones en la consistencia del líquido y lo que se conocía entonces como la fiebre epidémica y que hoy en día llamamos meningitis, ¿no? Y de hecho desde finales del XIX la punción lumbar es una técnica súper habitual para el diagnóstico de algunas enfermedades neurológicas, sobre todo las infecciosas, pero poco a poco se ha ido implementando también en otros contextos. Sin embargo, para la enfermedad de Alzheimer, hasta hace relativamente poco no se habían detectado alteraciones significativas, pero desde que empezamos a conocer un poco mejor los componentes de las placas amyloide, de los ovillos neurofibrilares, siempre hubo la sospecha de que el líquido cefalorraquídeo podía ser de utilidad si se buscaban las moléculas adecuadas. Bueno, hasta hace unos años, básicamente, el diagnóstico de la enfermedad de Alzheimer se basaba puramente en síntomas clínicos. Por un lado teníamos los síntomas clínicos de los pacientes que nos lo contaban en la consulta y por otro lado teníamos el diagnóstico neuropatológico que podíamos observar solo a través de la autopsia ya una vez al final de la vida de los pacientes, y los clínicos teníamos que intentar jugar a adivinar y a ver qué congruencia había entre estos síntomas clínicos y los síntomas neuropatológicos. Hoy en día el panorama, como sabéis, ha cambiado por completo y tenemos biomarcadores. Yo me centraré en los de líquido, pero luego tenéis una presentación también sobre marcadores de imagen y veréis cómo esto ha cambiado radicalmente la manera que tenemos de abordar a los pacientes. Pues bien, los principales marcadores diagnósticos para la enfermedad de Alzheimer, que son A-beta 42 o el ratio 42-40 como marcador de placas de amyloide, y también la proteína tau en su forma total o en la forma fosforilada como marcadores más de degeneración y de ovillos neurofibrilares. Y también se ha ido sumando últimamente la cadena ligera de neurofilamentos, NFL, que también os sonará como marcador de degeneración axonal. Todos estos marcadores se pueden medir en líquido cefalorraquídeo y sabemos por estudios transversales que en población sana, en ausencia de síntomas cognitivos, lo normal es tener niveles altos de A-beta 42 y de A-beta 42-40 y niveles bajos de tau y de fosfotau. Sin embargo, a medida que aparece la enfermedad de Alzheimer, a medida que se desarrolla la enfermedad de Alzheimer, este perfil de biomarcadores se invierte, incluso en fases previas al inicio de los síntomas, con lo cual si analizamos el líquido cefalorraquídeo en fases iniciales de deterioro cognitivo leve, ya veríamos un perfil invertido con descenso de beta 42 o 42-40 y un aumento de proteína tau y fosfotau. La manera de hacerlo es muy sencilla, realmente no tiene mucho misterio, es hacer una punción lumbar. Cuando hacemos una punción lumbar siempre se suelen recoger varios tubos, un tubo general en el que miramos bioquímica básica, recuento celular, y luego se suele recoger un tubo específico para biomarcadores, que luego hablaré un poquito de esto porque hay algunas particularidades aquí. Y respecto al procedimiento específico de la punción lumbar, no quería dejar pasar la oportunidad de recalcar la importancia del tipo de aguja que utilizamos para hacer la punción. Esto no tanto para los biomarcadores en sí, porque tampoco es que tenga una influencia directa sobre los biomarcadores, pero sí que hay mucha evidencia de que las agujas tipo punta de lápiz, como esta que veis aquí a la derecha, reducen mucho el riesgo de cefalea postpunción en comparación con estas otras agujas más cortantes o biseladas, ¿no? Entonces, siempre es recomendable utilizar este tipo de aguja como paréntesis clínico. El líquido normalmente lo congelamos porque no es habitual tampoco medir los biomarcadores a diario, paciente por paciente, sino que normalmente se espera tener un acúmulo de varios pacientes para medirlos en bloque. Se suelen congelar a menos 80 grados y luego se analizan. Hablaba del tipo de tubo porque es especialmente relevante en los marcadores de Alzheimer y específicamente en A-beta 42. Ya hay mucha evidencia que habla de que A-beta 42 es un péptido especialmente complejo desde el punto de vista físico-químico para trabajar con él desde el punto de vista analítico, y que tiene una adherencia particular por determinados materiales. Entonces, dependiendo un poco de qué tipo de tubo se utiliza, la adherencia puede ser mayor o menor, y esto influye en los resultados finales de la determinación. Y esto es una comparación muy simple que hicimos nosotros hace unos cuantos años, y realmente veíamos una diferencia de alrededor de un 30% en los niveles solo por el hecho de recoger el líquido en un tubo o en otro. Esto no es tan evidente para tau y fosfotau, donde son más o menos comparables, pero para beta 42 es especialmente significativo. Otro aspecto preanalítico a tener en cuenta, también ligado un poco con esto, es el volumen al que llenamos las alícuotas que recogemos. Una vez más, para tau fosfotau esto no tiene una implicación significativa, pero para beta 42 sí que hay también ya evidencia de que llenar el tubo hasta un cuarto, la mitad o por completo puede hacer que la determinación de beta 42 sea mayor, sea superior o inferior. Esto se corrige parcialmente si aplicamos un cociente con beta 40, es decir, beta 42-40, pero no del todo. Incluso aplicando el cociente se ven diferencias si llenamos el tubo más o menos. Una vez más, probablemente por estas propiedades físico-químicas y la diferente proporción entre el líquido que está en contacto con la superficie del tubo, ¿no? Que esto probablemente influya en la determinación final. Una tercera condición preanalítica que es importante tener en cuenta es el almacenamiento de este líquido. Como decía, no lo solemos analizar al momento, se suele esperar varios días hasta tener varios pacientes y analizarlos todos de golpe, y la manera en que almacenamos este líquido en este tiempo también puede condicionar la determinación de los niveles. Una vez más, no tanto para tau total y fosfotau, pero sí que para beta 42, el péptido más complejo de trabajar, sí que hemos visto que puede haber diferencias, sobre todo cuando se guarda en nevera, por ejemplo, durante 1 o 2 semanas, los niveles van decayendo. Por eso siempre se recomienda mantenerlo congelado, como mínimo hasta menos 20, si es a corto plazo, y lo recomendable sería menos 80 grados. En resumen, de condiciones preanalíticas, fijaos que hasta ahora solo he hablado de preanalítica, ni siquiera hemos empezado a hablar de los análisis en sí, pero sería importante tener en cuenta estas particularidades en los marcadores de Alzheimer. Usar siempre básicamente el mismo protocolo. A nivel interno en el centro, no hacer cambios de protocolos y no utilizar tubos distintos, que todo el mundo tenga claro cuál es el manejo. Aplicar siempre los mismos tubos, tanto de recogida como almacenamiento, que el volumen de alicuotado esté estandarizado en el laboratorio y siempre sea igual, que el tiempo de procesamiento también sea homogéneo entre todas las muestras y que las condiciones de almacenamiento sean lo más estables posibles y si puede ser a menos 80 grados. Y sobre todo tener en cuenta que si hay desviaciones o variaciones en este protocolo, en la recogida de una muestra particular, los valores de referencia pueden no ser aplicables. Entonces habría que tenerlo en cuenta, y eso a veces ocurre, que hay pacientes en los que los resultados no te cuadran y yendo hacia atrás te das cuenta que es que la muestra no se recogió adecuadamente y el valor no es del todo interpretable. Esto hay que tenerlo en cuenta. Si hablamos ya de los análisis en sí, de cómo se analiza, hasta hace unos años la técnica más habitual para analizarla era el ELISA manual. Estas técnicas todavía se utilizan a día de hoy, pero como entrañan una cierta variabilidad debido al factor humano de análisis, han sido prácticamente reemplazadas por plataformas automatizadas que ya están disponibles desde hace unos 4 o 5 años. Esas plataformas tienen varias ventajas. Por un lado, reducen este factor humano de variabilidad analítica y por otro lado también te permiten hacer análisis mucho más individualizados. Para hacer una placa de ELISA, lo habitual era tener que esperar a llenar toda la placa de ELISA con 30-35 pacientes, mientras que las plataformas automatizadas te permiten la opción de hacer una determinación individual o pocas muestras sin tener que esperar a tener tantos pacientes, con lo cual el retorno de resultados también puede ser más rápido. También ha habido un esfuerzo considerable para que los resultados de diferentes proveedores de estas plataformas automatizadas sean lo más comparables posible y de hecho se ha establecido un material de referencia certificado sobre el cual los diferentes proveedores tienen que referenciarse de manera que los valores así sean comparables entre plataformas, ¿no? Eso también permite una estandarización entre plataformas. La realidad es que la correlación entre el ELISA manual y las plataformas automatizadas es muy alta, pero sí que es verdad que las plataformas automatizadas tienen estas ventajas, ¿no? de análisis que puedes hacer en muchas menos muestras y la variabilidad y el factor humano quedan reducidos a la mínima expresión. Pues bien, realmente, claro, la utilización de biomarcadores tiene ventajas evidentes, ¿no? Y esto creo que en este foro de medicina de precisión no tengo que convencer a nadie. Sabemos que nos ofrecen evidencia biológica de la presencia de la enfermedad, que nos permiten distinguir entre lo que es la enfermedad de Alzheimer propiamente y otras causas de deterioro cognitivo que se pueden parecer desde el punto de vista clínico y nos permiten adelantar el diagnóstico a fases muy tempranas de la enfermedad. Y ya desde un punto de vista más de investigación, pueden ser una herramienta para medir los efectos biológicos de tratamientos dirigidos. Esto, pues, en estos días en los que han salido estas noticias tan recientes, ¿no? Es de especial interés, porque seguramente nos hará falta algún marcador biológico para medir la eficacia de los tratamientos biológicos. Y también nos permiten estudiar las vías fisiopatológicas de la enfermedad de Alzheimer, pero también de otras enfermedades. Sin embargo, no están exentos de limitaciones. La principal limitación es que se requiere una punción lumbar. Esto es una limitación relativa porque al final es una prueba diagnóstica como cualquier otra, pero es verdad que hay pacientes a día de hoy que todavía son reticentes a hacerse una punción lumbar, incluso hay clínicos que también son reticentes a hacer punciones lumbares, a pesar de que se ha demostrado ampliamente que es una técnica muy, muy segura, ¿no? Sobre esto sí que cabe recalcar la importancia que tendrán los biomarcadores en sangre, que como veréis en la siguiente presentación están ya aquí. Falta un proceso de implementación, pero están ya al llegar. Y otra limitación importante es que no tengamos puntos de corte universales, es decir, que los resultados que yo analice en San Pau me los puedo creer en San Pau, pero si lo recibe un médico de otro centro y solo ve el valor crudo, le será difícil interpretar si ese valor es normal o no, porque los puntos de corte y los valores de referencia pueden variar bastante entre centros. Esto se debe a estas variabilidades preanalíticas y particulares preanalíticas de cada centro y también a variedades analíticas, porque las plataformas que se utilizan en un centro y en otro pueden variar. Pues bien, ya sabemos cómo hay que recoger la muestra y cómo hay que guardarla, cómo se analiza. Y es importante también saber cuándo tenemos que acceder a este tipo de herramientas. Y aquí me remito a las guías de la Sociedad Española de Neurología, que al final recogen también el consenso internacional en este aspecto. Y todas las guías establecen que tiene que haber unas condiciones previas antes de plantearnos si podemos o no medir biomarcadores en un paciente en concreto, ¿no? Y estas condiciones previas es que tiene que haber un déficit cognitivo documentado de manera objetiva. Tenemos que estar ante una situación donde el diagnóstico etiológico no esté claro, donde el Alzheimer sea una posibilidad, pero puede que nos estemos planteando otras opciones, incluso después de haber sido evaluado por una persona experta en demencias, y donde se espera que la certeza diagnóstica o el tratamiento puedan cambiar por el resultado del marcador, ¿no? Si se cumplen estas tres condiciones iniciales, entonces es cuando tenemos que empezar a plantearnos si estaría indicado o no utilizar un biomarcador. Y las indicaciones principales que se recogen en la mayoría de guías son estas tres que veis aquí. Una sería el caso de deterioro cognitivo ligero, persistente o progresivo, donde la causa no esté clara. Y esto es precisamente para hacer el diagnóstico de enfermedad de Alzheimer prodrómica, ¿no?, en las fases más iniciales. Todas las guías ponen un criterio de edad, que obviamente no es un criterio rígido, sino que hay una cierta arbitrariedad en este criterio. 75 podrían ser 74, 76, 72, no hay que ser especialmente rígido. Pero esto es importante porque sabemos que a mayor edad el valor predictivo positivo de los biomarcadores disminuye. No porque el marcador sea mejor ni peor, sino porque es más frecuente que se sumen otras causas, otras patologías a nivel cerebral, causas vasculares, depósitos de otras proteínas, etcétera, que pueden también contribuir al deterioro cognitivo, de manera que la contribución de la proporción de Alzheimer que pueda tener ese paciente en particular puede ser menor a edades más avanzadas, ¿no? Mientras que en edades más jóvenes el papel de la fisiopatología Alzheimer está más claro. Otra indicación sería en pacientes con un curso atípico, presentaciones atípicas o mixtas, por ejemplo, presentaciones más visoespaciales o más conductuales, por ejemplo, más de lenguaje, donde el Alzheimer no es el curso típico o habitual de la enfermedad de Alzheimer. Y también en demencias de inicio temprano, principalmente por las implicaciones que pueda tener a nivel sociofamiliar el hecho de hacer un diagnóstico de enfermedad de Alzheimer a estas edades. También es importante conocer cuándo no está indicado utilizar marcadores fisiopatológicos. Y aquí he recogido algunas de las no indicaciones, no son contraindicaciones, son no indicaciones, pero creo que es importante tenerlo claro también para saber cuándo no nos aportan un valor añadido. La primera es en pacientes con enfermedad de Alzheimer probable típica con edad de inicio típica. Y esta veréis que la he puesto entre paréntesis porque es verdad que las guías recogen esto como no indicación, porque hasta a día de hoy no nos cambia el manejo. Un paciente con una presentación típica y una edad típica lo vamos a tratar igual, tanto si el marcador es positivo como si es dudoso, porque lo trataremos como si fuera una enfermedad de Alzheimer. Lo he puesto entre paréntesis porque seguramente esto haya que revisitarlo en presencia de un tratamiento modificador de la enfermedad, ¿no? Si lecanemab o cualquier otro de los fármacos que están en el pipeline se aprueba, seguramente querremos tener una evidencia fisiopatológica de la presencia de la enfermedad antes de aplicar un tratamiento de este tipo, ¿no? Y por eso lo he puesto entre paréntesis, porque seguramente esto en los próximos años pueda cambiar. Tampoco está indicado utilizar marcadores fisiopatológicos para evaluar la gravedad de la demencia. La gravedad de la demencia se evalúa con criterios clínicos y con medidas clínicas y cognitivas, no con un biomarcador, al menos a día de hoy, o al menos los que tenemos disponibles a día de hoy. Tampoco está indicado a nivel asistencial utilizarlos en sujetos asintomáticos o que no tengan un déficit cognitivo objetivo en la exploración. Ni siquiera cuando hay una historia familiar de enfermedad de Alzheimer o personas positivas, APOE4 positivas, ni siquiera en esas situaciones estaría indicado a nivel asistencial utilizar biomarcadores. A nivel asistencial, ya digo, otra cosa es investigación y otra cosa, un panorama muy distinto, será si hay también un tratamiento biológico que sea implementable en fases preclínicas de la enfermedad. Pero a día de hoy, así es como están las cosas. Y obviamente tampoco está indicado para usos no médicos, para usos legales, coberturas de seguros o cribados de salud. Eso tampoco es una indicación médica para utilizar estos marcadores. Pues bien, también creo que es fundamental que tanto el paciente como la familia, como el propio personal clínico, sepa qué puede esperar de los resultados de los marcadores que tenemos a día de hoy, ¿no? Nosotros en San Pau, a todos los pacientes a los que les proponemos hacer una punción lumbar para los biomarcadores, siempre les explicamos esto antes de hacer la punción lumbar. Les explicamos los posibles escenarios en los que podemos encontrarnos cuando venga la visita de resultados, ¿no? Y les explicamos que puede haber un resultado negativo, en el cual excluimos prácticamente al 100% la posibilidad de que exista una enfermedad de Alzheimer. Sin embargo, es importante que entiendan que esto no excluye otras enfermedades incluso neurodegenerativas, ¿no? Por ejemplo, la frontotemporal, la demencia con cuerpos de Levy o otro tipo de enfermedades, ¿no? Porque nos hemos encontrado algunos casos de pacientes con biomarcadores negativos y que luego con la evolución han desarrollado otro tipo de enfermedad neurodegenerativa, incluso más graves que lo que podía ser la enfermedad de Alzheimer. Es decir, que esto es importante que lo tengan en cuenta tanto los clínicos como pacientes y familias antes de la punción lumbar. Les informamos que un resultado positivo de alguna manera es una confirmación del diagnóstico de la enfermedad de Alzheimer y que en un contexto de deterioro cognitivo ligero esto es un diagnóstico de enfermedad de Alzheimer prodrómica. Y por otro lado, esto nos permite también tener la certeza de este diagnóstico y manejar la enfermedad de una manera muy distinta, tomar medidas también a nivel social, de voluntades anticipadas, de decisiones que se pueden tomar en fases muy iniciales de la enfermedad. Pero también les explicamos que puede ocurrir que vengan a la visita de resultados y les digamos que el resultado no es ni blanco ni negro, sino que es no concluyente. Esto en nuestra experiencia ocurre alrededor de un 15% de las veces y la experiencia que tenemos es que este es un grupo muy heterogéneo de pacientes que pueden ser desde otras enfermedades neurodegenerativas en las cuales hay un componente de fisiopatología Alzheimer, pero que la detección no es del todo clara, o formas atípicas de la enfermedad. Y en estos casos lo que hacemos es priorizar el criterio clínico y hacer un seguimiento también clínico de los pacientes y tratarlos en base a los criterios clínicos. Esto no nos ocurre mucho, pero sí que 10-15% de las veces lo vemos. Y también es bueno que pacientes y familias lo sepan de antemano, porque así saben qué esperar también en la visita de resultados. Bien, habréis notado que he hablado antes de A-beta 42 y del ratio 42-40, y esto es porque estas dos medidas se han utilizado como medida de amiloidosis en la mayoría de criterios de investigación y estudios de investigación se utilizan indistintamente como medida de amiloidosis, aunque a día de hoy ya hay bastante evidencia de que no son exactamente iguales y que incluso la concordancia no es perfecta entre estas dos medidas y sabemos que hay alrededor de un 20% de pacientes que pueden tener A-beta 42 alto y el ratio bajo o al revés. Y lo que sí que sabemos es que la medida del ratio, el 42-40, probablemente porque corrige alguna de estas variaciones preanalíticas, pero también porque seguramente refleja mejor la amiloidosis cerebral, concuerda más y se asocia mejor con medidas de tau y fosfotau y tiene una mayor asociación también con la progresión clínica de los pacientes. Sabemos que cuando el ratio está alterado, la progresión es peor que cuando el ratio es normal, indistintamente de que A-beta 42 aislado sea alto o bajo. Es decir, que son medidas que hasta ahora se han utilizado indistintamente, pero cada vez hay más evidencia de que el ratio es una medida más precisa de amiloidosis y que correlaciona mejor también con medidas de depósito de amiloide cerebral. Bien, y quería mencionar también qué ocurre con estos marcadores de Alzheimer en otros contextos y también mencionar muy brevemente a otros marcadores que se están desarrollando o que se han desarrollado en líquido cefalorraquídeo. En concreto, los marcadores de Alzheimer en el contexto de la demencia con cuerpos de Levy tienen baja precisión y de hecho sabemos que cerca de la mitad de los pacientes con demencia con cuerpos de Levy tienen marcadores positivos de enfermedad de Alzheimer, lo cual no es sorprendente porque la realidad es que la neuropatología dice lo mismo. Sabemos que entre el 50 y el 80% de pacientes con enfermedad con grupos de Lewy tienen copatología asociada de enfermedad de Alzheimer, con lo cual los marcadores simplemente es un reflejo de lo que ocurre a nivel cerebral. Lo que sí que sabemos es que los pacientes con demencia con cuerpos de Lewy que tienen biomarcadores positivos de enfermedad de Alzheimer tienen una peor evolución, tienen peor rendimiento en memoria, tienen alucinaciones con más frecuencia, tienen un declive más rápido y tienen incluso tasas más altas de institucionalización y de mortalidad. Es decir, que el pronóstico de estos pacientes es peor que si tuvieran biomarcadores de Alzheimer negativos. Los marcadores de líquido también nos han permitido caracterizar fases preclínicas de la enfermedad, y este es un estudio que hicimos hace unos años en colaboración con varios centros y en el cual también participó Valdecilla, y que nos permitió ver qué ocurría con otros marcadores o marcadores de otras vías fisiopatológicas en las fases preclínicas de la enfermedad, ¿no? Y por ejemplo vimos que algún marcador de inflamación, como por ejemplo IKL40, ya se elevaba desde fases preclínicas de la enfermedad. Antes de que empiecen a aparecer los síntomas, ya podemos detectar alteraciones en este tipo de marcadores. También me gustaría mencionar algunos ejemplos de otros marcadores que pueden tener una potencial aplicación tanto para el diagnóstico de algunas enfermedades como para el estudio de vías fisiopatológicas. Y uno de los más conocidos es la cadena ligera de neurofilamentos, o neurofilament light, que ha tenido mucha repercusión en sangre, pero que también tiene su utilidad desde el punto de vista de líquido cefalorraquídeo. Y lo que sabemos de este marcador es que es un marcador que lo que marca es destrucción neuronal, básicamente. La proteína neurofilamentos es una proteína axonal y cuando hay destrucción de esos axones se libera de manera inespecífica. Y los niveles más altos se ven en enfermedades como la ELA o algunas formas de demencia frontotemporal, pero se eleva en general en cualquier enfermedad neurodegenerativa o incluso no neurodegenerativa, un ictus, la esclerosis múltiple, un tumor cerebral puede provocar una elevación de neurofilamentos en líquido cefalorraquídeo. En relación con estos otros marcadores, también en otros contextos como la degeneración lobular frontotemporal, hemos visto que hay algunos marcadores que pueden tener también bastante precisión para detectar esta enfermedad. Y en concreto, la combinación de este marcador, que es ese APP-beta, que es un fragmento del procesamiento de la proteína precursora del amiloide, con este otro marcador inflamatorio que mencionaba antes, IKL40, si los combinamos, sabemos que esto tiene una alta precisión diagnóstica para distinguir la enfermedad, la degeneración lobular frontotemporal en diferentes síndromes asociados de personas sanas y también de la enfermedad de Alzheimer. Y esto lo hemos visto en una cohorte clínica, pero también en cohortes con confirmación neuropatológica, es decir, que tienen un cierto potencial que podrían ser implementables en el futuro. Otro ejemplo podría ser este otro marcador, NPTX, que es un marcador de disfunción neuronal, disfunción sináptica, que también se altera en fases incluso preclínicas. Esto es un estudio que hicimos en personas con síndrome de Down, en el cual ya había alteraciones en fases previas al inicio de los síntomas de la enfermedad de Alzheimer. Incluso había asociaciones con otros marcadores de la enfermedad de Alzheimer, como medidas de amyloidosis cerebral o atrofia cerebral. Y también me gustaría mencionar esta otra técnica que también yo creo que veremos que va ganando importancia en el futuro por su potencial aplicación, que es los sistemas de amplificación de proteínas in vitro, que eso es lo que también se conoce como RT-Quick o PMCA, tiene diferentes nombres, que básicamente consiste en poner en contacto una muestra con un sustrato recombinante y esta combinación, esta interacción puede favorecer la conversión de esta proteína recombinante a una forma mal plegada. Esto sirve sobre todo para detectar enfermedades en las que hay un comportamiento de proteínas mal plegadas y esta agregación se fracciona y luego el ciclo vuelve a empezar, de manera parecido a lo que sería una PCR, pero amplificando una proteína, ¿no? Esto tiene ya mucha utilidad en el diagnóstico de enfermedades priónicas, pero también se está empezando a utilizar en enfermedades de otro tipo. Por ejemplo, las sinucleinopatías es donde ha ganado mucha relevancia y es posible que en el futuro se implemente en otro tipo de enfermedades también. En concreto, en las sinucleinopatías, aquí veis un poco los ciclos de amplificación. Es una técnica que tiene algunas triquiñuelas desde el punto de vista técnico, pero esto dificulta un poco su universalización, pero que funciona bastante bien cuando funciona, ¿no? Y lo que se ve es que las personas que tienen estas formas de sinucleína con tendencia a agregarse tienen esta amplificación de la proteína, y las que no tienen la enfermedad no amplifican esta proteína, ¿no? Y esto permite el diagnóstico físico-químico, fisiopatológico, digamos, de las sinucleinopatías. Esto se ha probado en pacientes con enfermedades con cuerpos de Levy, pero también con enfermedad de Parkinson. Incluso también se ha detectado en personas con trastorno de conducta de sueño REM idiopático, es decir, que todavía no han desarrollado ningún síntoma de parkinsonismo ni otros síntomas de sinucleinopatía, pero sí que se detecta ya positividad en esta técnica de RT-QuIC en líquido cefalorraquídeo. Y esto puede tener muchas implicaciones a nivel diagnóstico, porque puede ser un marcador de mucha utilidad en este tipo de entidades. Incluso podría permitir también distinguir entre distintas sinucleinopatías, ¿no? Y, por ejemplo, parece que ya hay bastante evidencia de que las formas de agregación en distintas sinucleinopatías son un poco distintas, seguramente porque la conformación sea un poco distinta, y la agregación en Parkinson es distinta de la agregación en la atrofia multisistémica, por ejemplo, ¿no? Y esto a lo mejor puede permitirnos también distinguir entre diferentes parkinsonismos o hacer el diagnóstico diferencial. Pues bien, en conclusión, y con los puntos clave con los que me gustaría que nos quedáramos en esta presentación, es, por un lado, que el diagnóstico de la enfermedad de Alzheimer con apoyo de biomarcadores del líquido cefalorraquídeo es una realidad, ya lo es desde hace unos cuantos años. Nos falta un poco el proceso de implementación universal, no está accesible en todos los centros, pero cada vez está accesible en más sitios. Para esto ha ayudado mucho la automatización de la técnica, y es muy importante cuando se utilicen estos marcadores tener en cuenta las condiciones preanalíticas que mencionaba antes y tener muy claro qué información podemos esperar de los biomarcadores, qué información nos aportan desde un punto de vista clínico y un punto de vista diagnóstico. Como segundo punto importante, recalcar que los marcadores, tanto los que ya tenemos disponibles asistencialmente como los que son más en contexto de investigación, nos aportan información fisiopatológica de la enfermedad, y que esto nos ofrece un valor asistencial añadido tanto desde el punto de vista diagnóstico como probablemente en el futuro desde un punto de vista pronóstico. Nos permitirán monitorizar mejor la evolución de los pacientes. Y también nos permitirán optimizar los tratamientos modificadores que también están a la vuelta de la esquina. Y por otro lado, el último punto, recalcar que aparte de A-beta 42, 40, tau y fosfotau, tenemos también marcadores para demencias no Alzheimer que también son muy prometedores y que probablemente en los próximos años veamos cómo se van implementando. Nada, simplemente presentar al equipo de San Pau, que también ha participado en muchos de los estudios que he utilizado para ilustrar un poco esta presentación. Y nada, a partir de ahora, si tenéis alguna pregunta, alguna duda que pueda contestar, estaré encantado. Gracias.
Muchísimas gracias, Dani, por esta charla tan didáctica, tan clara, tan interesante. Tenemos alguna pregunta en el chat. ¿Crees que NFL debería ser incluido ya de rutina en el análisis de pacientes con sospecha de Alzheimer en la clínica habitual? Y si la respuesta es negativa, ¿qué nos faltaría para hacerlo?
Vale, es buena pregunta, ¿eh? Sí que es verdad que NfL es un marcador que ha ganado muchísimo protagonismo. Ya hace unos cuantos años que en líquido cefalorraquídeo se puede medir, pero donde ha ganado más protagonismo es en el plasma, y esto lo oiréis en la siguiente presentación, y es porque es detectable en plasma, correlaciona muy bien las medidas de plasma con las de líquido, entonces ahí es donde creo que va a jugar un papel más importante. En líquido cefalorraquídeo es verdad que lo podríamos también medir, lo que pasa es que el valor que tiene es muy inespecífico. El valor que tiene ahí, al ser tan inespecífico, queda más limitado, porque para empezar no tenemos unos puntos de corte estandarizados, no está disponible a día de hoy su medida automatizada, hay que hacerlo con técnicas más bien manuales, y la información que puedes obtener de ahí, sobre todo sin tener puntos de corte en las que puedas dicotomizar positivo o negativo, es muy reducida, ¿no? No te responde a la pregunta de si puede tener un Alzheimer o no, porque se puede elevar en otras demencias, en un ictus, en otras enfermedades. Y creo que no tiene una implementación clínica directa a día de hoy. Sí que puede tener uso en otros contextos. Por ejemplo, seguramente nos pueda servir para monitorizar a lo mejor, pero esto no está todavía validado y nos falta información para poderlo utilizar como monitor de la evolución de la enfermedad.
Tenemos otra pregunta también en el chat. Es tu opinión sobre la participación de los centros en programas de quality control de la Alzheimer Association. ¿Qué te parece?
Bueno, creo que es fundamental. Creo que es fundamental por varios motivos. Uno es para saber cómo estamos, porque no sé si muchos de los que estáis aquí participáis en algún programa de este estilo, pero si lo hacéis, veréis que cuando recibís los resultados, bueno, un poco para contexto, este programa de control de calidad, básicamente, por ejemplo, que organiza la Asociación de Alzheimer en colaboración con la Universidad de Gotemburgo, lo que hacen es preparar muestras cada año y envían la misma muestra a todos los laboratorios que participen. Y cada laboratorio la analiza 3 veces al año y devuelve el resultado, de manera que luego tú sabes si tu resultado está igual, más alto o más bajo que el de otros centros, ¿no? Y lo que se ve en estos resultados es que la variabilidad analítica que hay entre centros es altísima. Realmente los valores un centro puede tener valores de 300 y otro casi de 500 o 600, que es a nivel intercentro hay mucha variabilidad, aunque a nivel intracentro la consistencia de tus marcadores sea muy alta, ¿no? Pero sí que te permite saber hasta qué punto tus valores son comparables con los de otros centros. Entonces yo creo que participar en este tipo de estudios y de programas es fundamental para saber dónde estás.
Estupendo. Yo tengo alguna pregunta para Dani. Me gustaría llevarte ahora al futuro, ¿no? En un futuro en el que ya tenemos un fármaco que se aplica a nuestros pacientes. ¿Cuál crees tú que sería el papel del análisis de líquido cefalorraquídeo en este contexto? ¿Qué utilidad podría tener? Si podría tener utilidad o vamos a usar el PET y la resonancia y el líquido va a jugar un papel secundario. ¿Cómo lo ves tú?
Buena pregunta. Yo creo que va a haber diferentes contextos, probablemente. También aquí dependerá mucho de la accesibilidad que cada centro tenga a hacer punciones lumbares o a hacer un PET, por ejemplo. Desde luego, si fuera un tema de coste-eficiencia, el líquido sería mucho más rentable, porque con el coste de un PET puedes analizar alrededor de 20 pacientes con todos los marcadores. Es decir, que realmente a nivel de eficiencia sería mucho más eficiente hacer una punción lumbar, pero dependerá un poco del contexto. Yo creo que sí que necesitaremos cada vez más tener evidencia fisiopatológica de la enfermedad, es decir, que esto que ponía antes entre paréntesis de pacientes típicos con demencia típica, creo que cada vez más vamos a tener, incluso en esas situaciones, que confirmar biológicamente la presencia de la enfermedad. Y por un lado, para mejorar el diagnóstico, pero también yo creo que tendremos que utilizar los marcadores para monitorizar el efecto de los fármacos también. Independientemente de que hagamos resonancias para detectar si hay áreas o no hay áreas o otro tipo de efectos secundarios, seguramente los biomarcadores, especialmente cuando nos movamos más hacia fases más preclínicas o sintomáticas muy iniciales, donde la monitorización clínica tiene menos rango dinámico, seguramente los marcadores biológicos irán ganando papel. No sé si los de líquido o ya tendremos los de plasma suficientemente avanzados como para empezar a hacerlos en plasma. Esto habrá que irlo viendo, pero desde luego hará falta tirar de biomarcadores seguro.
Un tema que a mí me parece muy interesante y que, claro, ahora mismo es ciencia ficción, ¿no? Es el riesgo de áreas, ¿no? O detectar precozmente las áreas, ¿no? Aparte de hacer resonancias magnéticas, ¿tú crees que ahí la punción lumbar puede jugar algún papel detectando algún tipo de fenómeno inflamatorio o alguna alteración en el líquido que refleje eso?
Yo creo que sí, yo creo que habrá que buscarlo, porque no estamos preparados para ir haciendo resonancias magnéticas con tanta frecuencia al volumen de pacientes que probablemente vayan a ser candidatos a este tipo de tratamientos, ¿no? Es decir, que seguramente habrá que buscar un marcador y primero habrá que validar cuál es la correlación de este marcador y su precisión diagnóstica para detectar este tipo de alteraciones. Y ya digo, aquí tengo dudas de si en líquido o en plasma, porque veo que los marcadores en plasma realmente están yendo rapidísimo y por accesibilidad y por facilidad de determinación y todo, creo que probablemente acaben avanzando para este tipo de usos a los marcadores en líquido, independientemente de que luego a lo mejor en unos casos concretos necesitemos la confirmación en líquido cefalorraquídeo. Pero para el grueso de pacientes, probablemente para temas de monitorización, de screening, cosas de este estilo, seguramente los de plasma ganarán la batalla, como probablemente comente el doctor Suárez en la próxima presentación.
Ahora se lo preguntamos a él. Muy bien, pues muchísimas gracias. Vamos a pasar al siguiente ponente, que es el doctor Marc Suárez. Marc es neurólogo clínico también, él trabaja en el Hospital del Mar como atendiendo pacientes y luego también dirige en Barcelona Beta la línea de biomarcadores sobre todo en plasma, ¿no? Donde él es una auténtica referencia internacional en este campo y tenemos la suerte con que nos va a hablar de lo que yo decía y comentaba también Dani, ¿no? Que es el futuro inmediato que son los marcadores de plasma. Cuando quieras, Marc.
Hola, buenas tardes, Pascual. Primero de todo, gracias, Pascual, Eloy y todo el grupo de Valdecilla por invitarme a dar esta presentación. So yeah, thank you very much to everyone to be here, and I've been very lucky to present the blood biomarkers talk with I believe is one of the hot topics now in the Alzheimer and neurodegenerative field. Actually, some of us started to work in biomarkers together with Dr. Alcolea in San Paulo many years ago, and some of us we were very skeptical about blood biomarkers. And we believed that CSF was the way to go. And actually, I still believe that CSF is the best biomarker. But during the last 2 years, really, the blood biomarkers field has changed so much. And now, finally, we really have very good blood biomarkers for Alzheimer's, not for other neurological diseases, but there are still a lot of things to do here, a lot of research to do here. So I will do an overview of the blood biomarkers, but I will try to be quite brief because I would like to present here some new unpublished data that we have from our center, and also some other data that we have just recently published this summer, because I think that this kind of meetings is the place to show new unpublished data. So these are my disclosures. So I will start, probably you have heard this in previous talk, but it's important to highlight the new concept of Alzheimer's disease as a biological concept, and also the importance of the continuum of Alzheimer's disease. I will talk a little bit about the type of biomarkers and what blood biomarkers we have for Alzheimer's disease and neurodegeneration. And then I will present here some new and published data from our center in Hospital del Mar regarding symptomatic Alzheimer's disease. And then I will focus especially in cognitively and impaired in preclinical Alzheimer's, with this, well, the main focus in Barcelona Beta Brain Research Center, which we really focus on the study of preclinical Alzheimer's disease. And I hope I will have some times in the very end to discuss some challenges in the blood biomarker research that I hope I can discuss it with you. So let's start from the very beginning. You probably know this very well. Alzheimer's disease is not a disease that starts suddenly one day. There's a very long continuum. Some years ago, in the clinics, we only saw those patients that have a dementia syndrome due to Alzheimer's disease or due to other neurological diseases. Then more lately, I think that we are starting to see people with mild cognitive impairment due to Alzheimer's disease, so prodromal Alzheimer's disease. But it's important also to remember, to keep in mind, there are people that are completely asymptomatic. They do not have any kind of symptom. They are cognitively unimpaired. And however, they start to have amyloid and tau deposition in the brain. And that's the biological definition of Alzheimer's disease. So whenever you have amyloid and tau in the brain, that is Alzheimer's disease. Maybe you don't have any symptom, but as it happens in many other diseases, that you start having the disease before the symptoms arise. And this long continuum can take 20, 30 years. This is very important when we discuss biomarkers, and particularly blood biomarkers, because the meaning of that biomarkers in these different stages may be different. And we may use some biomarkers in different stages for diagnosis, others in different stages for prognosis, and so on. So it's very important to keep in mind this continuum and these different stages of the disease. In fact, you all know the ATN classification, which is not a clinical classification, it's a biomarker classification, A for amyloid, T for tau pathology, and N for neurodegeneration. And we have these two axes of biomarker, the biological profile of the disease and the clinical profile of the disease. And these are two different things. So you can biologically have defined with biomarkers an Alzheimer's disease because you are amyloid and tau positive, but however being cognitively unimpaired. So really being in this preclinical stage of the disease. So it is important then, the terminology is important, and yeah, we have to clearly differentiate when we talk about the biological, the biomarker profile of the disease, and when we talk about the syndromic, the clinical presentation of the disease. So always keep in mind these two axes. So for the biomarker profile, we have CSF that still, I think that it is, and I believe that it always be the most important biomarkers for Alzheimer's disease and neurodegeneration. And now we have just heard the excellent talk of Dr. Alcolea, have excellent biomarkers for Alzheimer's disease. Actually, I believe that for the diagnosis of Alzheimer's disease, we do not need more CSF biomarkers. We need more CSF biomarkers to understand better the physiopathology, to tell information about the prognosis, about how to monitor the disease, especially now with the new biologic therapies. But we already have really, really good CSF biomarkers for the diagnosis of Alzheimer's disease. We have the neuroimaging biomarkers, and now we will have the blood biomarkers as well. But the blood biomarkers, we still need to know what kind of information they give to us. So we still need to understand a little bit more then. So my first take-home message of this talk is to keep in mind that Alzheimer's disease and all neurodegenerative diseases, frontotemporal dementia, Lewy body disease, Parkinson's disease, they have a long clinical course, and that includes a preclinical stage. And the different biomarkers that we have, CSF, neuroimaging, or blood plasma biomarkers, can give us different information depending on the stages on that continuum. So let's go to the blood biomarkers. So here there is a physiopathological classification of the mechanisms that underlie Alzheimer's disease. And here you have the three main mechanisms that actually match very well or correspond to the ATN classification. So the amyloid pathology, tau pathology, and the neural and axonal injury. And here, highlighted in red, we have the blood biomarkers that we already have for those physiopathological mechanisms. So we can now measure amyloid in blood. That was quite tricky and still is a little bit difficult because there are problems of robustness of these assays. However, some of these amyloid assays in blood work very, very well, and we can measure now amyloid in the blood. In my opinion, the most promising ones are all the tau, and in particular phospho-tau blood assays from different epitopes, from different phosphorylation, 181, 217, 231. These are really good biomarkers to detect Alzheimer's disease. and the immunogenes that there are, and there are now several immunogenes, work very, very, very well. And then we have the markers, neurofilament and total tau. These are markers that are not specific for Alzheimer's disease. Neurofilament was the first plasma biomarker that really worked, but is an unspecific biomarker of neural injury. And in most of neurological diseases, there is an increase of that biomarker to a higher or lower extent. Besides that, well, we have to keep in mind as well that there are other mechanisms that underline the Alzheimer's disease, like synaptic dysfunction, glial response, vascular injury. For those, we have very good CSF biomarkers, for example, for synaptic dysfunction and so on. But here we do not have yet really good blood biomarkers still. That's quite tricky here to develop blood biomarkers, for example, for synaptic dysfunction. Or for glial dysfunction or glial reactivity, what we find in blood may not reflect well what is happening in the brain, may reflect better other kind of inflammation that occurs in the periphery, not in the brain. A notable exception is plasma GFAP. Actually, plasma GFAP is probably the only biomarker that seems to work better in blood than in CSF. And plasma GFAP really is really associated with amyloid deposition, even in very, as I will show later, in early stages of the disease. So here in this slide you can see, in red, those plasma biomarkers that would say that we have now that work well. Then there are other biomarkers, blood biomarkers, that we still need to develop for the physiopathological mechanisms. Very important. When we talk about biomarkers, usually most of us will think about diagnostic biomarkers. So a biomarker that tell us if there is the disease or not. Or if we're talking maybe people that are cognitively unimpaired or asymptomatic, maybe we should use the term that are susceptible or there are risk biomarkers. And regarding diagnostic biomarkers, blood biomarkers, in the last 2 years, there have been seminal works from different groups that have shown that we really have very good and now plasma biomarkers to detect Alzheimer's disease. This is the paper from Thomas Karikari in the University of Gothenburg showing that plasma phospho-tau-181 is really increases in Alzheimer's disease, even in prodromal stages of Alzheimer's disease, and it really has a high area under the curve in order to discriminate Alzheimer's disease from other neurological diseases or from healthy controls. And this has been replicated in other courses. Here it's interesting to see the difference between blood phospho-tau-181 and neurofilament. Neurofilament, it is increased in many other neurological diseases, while phospho-tau-181 increases specifically in Alzheimer's disease, but not in other neurological diseases, in this paper by Thyssen et al. In Nature Medicine. The same phospho-tau-181 from the Biofinder group, very similar results, really showing that phospho-tau-181 in blood really is increased in Alzheimer's disease, but also in prodromal Alzheimer's disease, not only when you have a dementia. More recently, phospho-tau-217 also shows really, this is a paper also from the Biofinder group in JAMA, really a very, very, very high area under the curve in order to detect Alzheimer's disease and discriminate it from another neurological diseases. So, I mean, we can be very happy because we have really very good plasma biomarkers that are able to detect Alzheimer's disease. I'm showing here the phospho-tau assays because I believe that are the ones that not only work better, but also they are more feasible to use them in the clinics. But we have similar data with, for example, with amyloid, especially those mass spec assays developed by Randy Bateman group, and also on the University of Gothenburg, that really also work very, very, very well. And they're also not only mass spec, but amyloid beta immunoassays that also have a very high accuracy to detect Alzheimer's disease. The main issue with the amyloid immunoassays is that they are not very robust. That means that although the area under the curves is quite high, the difference between the two groups, the Alzheimer versus the controls, is not very high, and that means that small technical differences in the values may change in which group you fall into. And it is important to have very robust analysis if you want to use these plasma biomarkers in different labs all around the world. Dr. Alcolea already mentioned that for the CSF assays, sometimes we see a lot of differences between centers. So with the amyloid immunoassays, although they are really good, there's probably some problems of robustness in that sense, why I believe the phospho-tau assays are more robust assays. So the take-home message number 2 is that we have excellent blood diagnostic biomarkers for Alzheimer's disease. However, there are still some challenges. What happens with preclinical Alzheimer's disease? We have just been talking about the continuum of Alzheimer's disease, or the individuals that are at risk of Alzheimer's disease. How these blood biomarkers behave in the routine practice. They seem to work very well in research cohorts, in cohorts that are real cohorts of patients that we see, but in a very well characterized cohorts in research hospitals. So what happens in the routine practice? So probably we need to test these assays in more hospitals, even in primary care. We know that some of these plasma biomarkers are affected by some comorbidities, for example, renal function or body mass index. So this is something that we need to investigate. We need to do more studies in more diverse population. There are differences, some difference in sex and gender, also race, ethnicity. So we need to study more diverse cohorts and see whether the blood biomarkers behave the same. And the big question is whether blood biomarkers really will have an impact on the clinical management, because a blood biomarker can be useful to differentiate Alzheimer's disease or not, but this will change the clinical management of that patient. We will prescribe more drugs, we will ask more or less tests, will be the patients and their caregivers more reassured about the information that they will give to them. This we still do not know. We need to do clinical utility studies with blood biomarkers. So some data that I would like to present. This is unpublished data, actually. So this is a study that we performed in Hospital del Mar in the Biodegmar cohort. That is a cohort of patients that come to our cognitive decline of movement disorders unit. So all kind of patients, some patients with Alzheimer's disease, MCI, Parkinson's disease, frontotemporal dementia, vascular dementia, subjective cognitive decline, a mix of patients. That it's what I think most of us we see in our clinics. All of these patients that have been included, that are included in this study, have CSF, have lumbar puncture as part of our routine diagnosis. That's the test that we use for the biological diagnosis of Alzheimer's disease. And so what we did is to perform a head-to-head comparison of the main phospho-tau plasma assays. And actually we studied 9 different phospho-tau immunoassays in the same, exactly in the same samples and the same patients of Hospital del Mar. All of them are symptomatic, so we are now talking about symptomatic patients. So in the continuum, in the second part, we'll talk later about cognitively unimpaired. So people that come with symptoms in our memory clinic. So this is the demographics of the patients. So we studied 197, all of them with CSF, and actually we use as a standard of truth the CSF profile. So we measure with the Lumipulse platform amyloid beta 42, phospho-tau and total tau, and we previously computed the cutoffs that work better in our clinic. Before, Dr. Alcolea mentioned that there are some variability in the CSF biomarkers, and sometimes these cutoffs are not universal, and each of the centers have to establish their own cutoffs. So we did so, and actually the cutoff that worked better was the ratio of amyloid 42 phospho-tau 181. So we classified in a very simple way, all our cohort in this CSF profile with the CSF amyloid 42 and phospho-tau ratio. So we have this group of patients that do not have a CSF AD profile, while we have this group of patients that have a CSF AD profile. It's important to notice here that in each of this group, the clinical diagnosis may be quite different. So in this CSF non-AD profile, there are people with subjective cognitive decline, MCI, Lewy disease, vascular dementia, PSP, frontotemporal dementia, and even some people that were clinically diagnosed of Alzheimer's disease. That happens, that's the real world. And in the CSF AD profile group, so biological definition, we have different clinical diagnoses. We have many, of course, as expected. Alzheimer's dementia due to Alzheimer's disease, MCI due to Alzheimer's disease, so prodromal Alzheimer's disease, subjective cognitive decline. But then we have other clinical diagnoses, some Lewy disease, vascular dementia, even some PSP, but with a CSF AD profile. So what we did is, using this CSF profile as a standard of truth, is to do a comparison of these different 9 immunoassays. So we compare it really head to head. So here is a kind of competition, which one is better. Luckily, there are many that are really good. So as the data is not yet published, I cannot show you, although it's not difficult to guess which company is each of these biomarkers. But here the good news is that here in the horizontal axis, you have the area under the curves, and some of these immunoassays, blood phospho-tau immunoassays, really have an area under the curve that is above 0.9. So they are really good, and they behave similarly to their CSF counterpart. So here there are the CSF assay compared to this plasma, the same plasma immunoassay. And some of them, especially these 4, are really good, and they have a high discrimination accuracy to discriminate between biologically defined with CSF AD versus non-AD defined by the CSF. There are others that are quite good, so are under the curves around 0.8, and there are others that do not behave so well. But I think that the good news is we have not one, but many phospho-tau immunoassays that I think that are ready to go to the clinics, because they perform very, very well, almost, and I say almost, as well as the CSF. Still, I believe the CSF is, and it will always be the standard of truth. But we have very good plasma biomarkers. This is regarding diagnostic biomarkers. But here, there's still a challenge about other kind of biomarkers. It's, again, important to remember that when we talk about biomarkers, it's not only about diagnostic biomarkers, but biomarkers can give us other information. They can give information about the stage of the disease, for example, while in the continuum IU. They can give us some information about the prognosis. So depending on the levels of that biomarker, whether you will progress quicker or slowly, or there will be some clinical event. Predictive biomarkers, which is not the same as prognostic. So here there is a kind of intervention, and we'll see which patients will respond better or worse to that intervention. That will become extremely important in the very near future when we have biological therapies. Maybe we have to detect those patients that will respond better to anti-amyloid drugs. So having predictive biomarkers will be extremely useful. We don't have yet them. Also, now that we are in a new paradigm of Alzheimer's disease with biological therapies, we need response biomarkers that tell us what is the response of that particular patient to an intervention, to a drug, in terms of safety, pharmacodynamic, or of efficacy, and again also for monitoring a response to a treatment. Here, the plasma biomarkers compared to a CSF have the great advantage that we can sample them more easily. We can, of course, repeat lumbar puncture if needed, but that's something that, of course, we cannot do every week. We can take a blood sample every week. All right, so take home message number 3. So we do have excellent blood diagnostic biomarkers for Alzheimer's disease. However, we need more research to evaluate blood biomarkers as a stage, prognostic, predictive, response, and monitoring biomarkers. We have to do more research on that, not only focusing on diagnostic of Alzheimer's disease. What we have to do regarding the diagnosis is to try to develop not only plasma but CSF biomarkers for other neurological diseases. We don't have good biomarkers for the temporal dementia, Lewy body disease, and so on. So that's probably where we have to focus now the research regarding diagnostic biomarkers. So now let me shift to cognitively unimpaired in individuals. So I show you at the very beginning the continuum of Alzheimer's disease, and at the beginning I'll talk to you about this symptomatic stage, either mild cognitive impairment or dementia. I just show you that we have very good biomarkers to detect Alzheimer's disease in symptomatic stages, and I show you some of our new data in Hospital del Mar regarding phospho-tau immunoassays. But what happens in cognitively unimpaired individuals, people that are asymptomatic, but some of them are in the preclinical stage of Alzheimer's disease, defined biologically because there is amyloid and tau pathology in the brain. So this is, in fact, the focus of Barcelona Beta Brain Research Center, the research center of Pasqual Maragall Foundation. In the hospitals, many of us are clinicians, we obviously see the patients that are symptomatic because they come to us because they have some kind of symptom. And they may have Alzheimer's disease or neurological disease or other neurological diseases, or maybe do not have anything, but they have some kind of symptom, and that's why they come to see us. However, the people that are symptomatic do not go to the doctor. However, they may be in a preclinical stage. So how do we study this preclinical stage? So in Barcelona Beta, 10 years ago, we started this project, which is called Alpha Study, that are almost 3,000 cognitively unimpaired individuals. Some of them are in the preclinical stage of Alzheimer's disease, actually approximately a third of them. And we know that because of the biomarkers, because to some of them we did CSF and blood. So this is the big Alpha study that we visited these participants, almost 3,000 10 years ago, and only a subgroup of them, what we call the Alpha Plus, which is around 400, are those participants that we have been followed during all this time, every 3 years, and they are very comprehensively characterized because we have CSF, we have amyloid PET, we have FDG PET, we will have now tau PET, we have, and now we have blood biomarkers. So all the data that I will show you is regarding this Alpha Plus. However, I have to say that these participants, these 2,743 that were visited 10 years ago, we took a blood sample at that time, and this blood sample was kept during 10 years in the biobank of our hospital, just waiting to have something that we can measure these blood samples. And now we have the blood biomarkers, and now we will start studying together with Marc Campo, who is the head of the facility of biomarkers in Barcelona Beta. We will measure all these thousands of samples to detect preclinical Alzheimer's in this big cohort. But we haven't done anything from the biomarker perspective in this big cohort. All the data I'll show you will be here in the Alpha Plus. So 2 years ago, we described that in CSF, not yet in plasma, the phospho-tau with the phosphorylation in 231, it seems that it was the one that increased earlier in the continuum of Alzheimer's disease. So this is a modeling of the changes of different biomarkers in preclinical Alzheimer's disease, because all these are Alpha Plus, cognitively unimpaired, these are not symptomatic patients, and the horizontal axis, we have amyloid PET centiloids. So the higher the centiloids, more amyloid uptake. So this is a kind of a proxy of the temporal evolution of preclinical Alzheimer's disease. Again, preclinical Alzheimer's disease, it takes 20 years. So it's so there are some people in preclinical Alzheimer's disease that they have a lot of amyloid accumulation, and they are very, very close to shift or to progress maybe to the symptomatic stage, and the other people that they have very subtle amyloid deposition in the brain, and it may take still even more 20 years, so they really start to have some symptoms. So this this amyloid PET centiloid scale is useful for us as a temporal proxy of this preclinical stage. And as you see here, this orange or yellow line is phospho-tau 231 in CSF, not in plasma, and is the one that increases steeper and earlier in the continuum of Alzheimer's disease. And then this is followed by 181 and also phospho-tau 217, while the others, neurofilament and here in blue, or total tau, they increase later. In that study, that was 2 years ago, we started to have some blood biomarkers. It's interesting to see how things have changed a lot in 2 years. And here we already include plasma neurofilament and plasma phospho-tau 181, that they increase during the continuum of Alzheimer's disease, but they do not reach abnormal levels in that stage. So what we did, and it was now just published this summer in Nature Medicine. So together with the University of Gothenburg, the team of Kai Bleno and together with Nick Ashton, so we developed a biomarker for phospho-tau 231, and we measured phospho-tau in our alpha plus cohort together with phospho-tau 217 and other blood biomarkers, all these biomarkers that you have here. So phospho-tau 181, 217, 231, GFAP, NFL, and also amyloid 4240. And so what we see was the following. So here there is the 6 plasma biomarkers. Now we are already in blood, we are in plasma biomarkers. And as you see here, let's focus in this plot here. So you have here like 3 groups. This one is those groups that are both CSF and PET amyloid negative. So they are really negative, they are not in the preclinical stage of Alzheimer's disease. Here in purple, you have participants that the CSF and the PET both are positive for amyloid. So they have clearly amyloid in the brain, as shown by the main 2 biomarkers, PET, amyloid PET and CSF. But in the middle, we have what we call the low amyloid beta burden. So these are these participants that they have changes in CSF that start to change first, but not yet clear positive amyloid PET. So they are in this kind of a transition between you are becoming CSF, you become CSF positive, so there is some kind of soluble amyloid changes, but there is not clear overt amyloid aggregated pathology as shown by amyloid PET. And what we see is that most of these biomarkers in this very, very, very early stage of the disease are significantly increased. However, the degree of change are quite different depending on the biomarker, and it's phospho-tau 231, the one that has a higher increase in that group, because there is an increase of almost 40% in that group, which is higher than any other plasma biomarker. So what we did is to model again all these changes of plasma biomarkers as a function of amyloid PET uptake. This is the centiloid scale, and what we see is the following thing. So we have plasma neurofilament. We already mentioned that plasma neurofilament was the first plasma biomarker to be developed. It's an unspecific biomarker for Alzheimer's disease. It is increased in any disease with neurological damage. And what we see is that in preclinical Alzheimer's disease, it does increase, but it does increase too much, and actually it does not reach abnormal levels. Then we have plasma phospho-tau 181 that also increases, but not too much. Then we have plasma amyloid beta 4240. This is the SIMOA assay, followed by plasma GFAP, that it does increase really in early stages of the disease. I think actually it increases even more than the CSF GFAP. And actually when you have around 65 amyloid PET centiloids, these levels reach an increase of 2 standard deviations that we define here as an abnormal levels. Same happens with plasma phospho-tau 217, really a very early plasma biomarker in preclinical Alzheimer's disease. And then we have plasma 231 that also, well, together with 217 are those that increase earlier, or we should say that reaches the higher levels with a lower amyloid PET uptake. This is of course cross-sectional. So we have to take this data cautiously. We need more longitudinal analysis, but I think that this data clearly showed to us that there are some plasma biomarkers that really starting to increase very early in the continuum of Alzheimer's disease, when you only have really some subtle amyloid deposition. And I think this is a very good news. Actually, here there is in this graph you can see the association of each of the plasma biomarkers with amyloid PET uptake at box cell level, and it's phospho-tau 231, 217, and to a lesser extent GFP, the ones that have a stronger association with amyloid deposition in the brain. And I insist, these are cognitively unimpaired individuals. These are not people that we see in the hospital because they have dementia or even MCI. They are cognitively unimpaired, but some of them have amyloid deposition, and these plasma biomarkers really indicate quite well these subtle changes in amyloid deposition in this very early stage. So we have to say, however, that when we calculate the area under the curve, so the discrimination accuracy of this biomarker alone, it's not very high. For example, for 231 or 217, it's around 0.7 something. So they are not have a very high accuracy for preclinical Alzheimer's disease, at least in the alpha cohort, which is a very, very early cohort. Maybe in other cohorts of preclinical Alzheimer's disease, when you have participants that are closer to start the symptoms, maybe this accuracies may be higher. But we have a very, very early cohort. And these biomarkers are not great when we use it alone to detect preclinical Alzheimer's disease. When we do the combination of this plasma biomarker with some risk factors like age, sex, and ApoE4, then the accuracy increases. And we have, for example, 231 that is, or 217, that they have an area under the curve to detect preclinical Alzheimer's disease, as defined by CSF, by the way, around 0.8. So that improves the accuracy. Also, I think something that we studied is to see the difference between younger and older people. I think this is quite relevant, especially for clinical trials. If we want to do clinical trials in middle-aged people or in older people, the biomarker that we may use for the prescreening of the population may be different. And actually, we see different results. So in the younger group, biomarkers like phospho-tau 231 or even amyloid 4240 have higher are in the curves, while in older people, there are several biomarkers, but especially 217 that have higher are in the curves. So probably we would need to use different plasma biomarkers depending on the population to study. If younger, older, in the very, very early stage of the early preclinical stage, or in the later stage of the preclinical stage, probably we need to use different biomarkers. It's not only about diagnosis, I mentioned that at the very beginning, it's also about prognosis. And actually we had some longitudinal data, and what we observed, and that's I think quite interesting, is that in people that are amyloid positive, as defined by CSF, people with higher levels of plasma phospho-tau 231, these higher levels of plasma phospho-tau 231 were associated with a higher cognitive decline as defined by the PAC composite. Again, these are cognitively unimpaired individuals. So these are people that are not progressing to MCI. They are still cognitively unimpaired. But even in the category of cognitively unimpaired, there are some variability in the cognition. And if we use some sensitive tests like the PAC, we can detect these subtle cognitive changes. And phospho-tau 231, the basal levels of phospho-tau 231 in blood are really associated with the cognitive decline after following 3 years in this cohort. This does not happen with the rest of the biomarkers. The interaction term between amyloid negative and positive, it's only significant with phospho-tau 231. Not only this, but we also studied and checked whether these plasma biomarkers predict more amyloid deposition at the follow-up 3 years later. In Alpha Plus, we see our patients every 3 years. And again, here is data from phospho-tau 231. In red, the amyloid positive participants. In green, the amyloid negatives. So what we see, the higher levels of plasma phospho-tau 231, then you have higher annualized centiloids change in amyloid PET. So these baseline levels predict more amyloid deposition in the future. Still in the preclinical stage of Alzheimer's disease. That also happens with 217. So phosphorylated 217 and 231s are those biomarkers that are able to predict this amyloid change. In fact, we did a sensitivity analysis, and we did here is to do the same analysis, so association between plasma biomarkers and annualized amyloid PET centiloid change, but only in those individuals that they have an amyloid PET uptake of less than 30 centiloids. So in people that do not have yet clear overt amyloid pathology. So because we wanted to see in this early stage of preclinical stage what happens, and in these people without a clear amyloid deposition, higher levels of these two biomarkers predict more amyloid accumulation at the follow-up after 3 years. So take home message here. So we have that phosphorylated 231, phosphorylated 217, and G5P reach abnormal levels with the lowest amyloid beta burden. Plasma biomarkers alone do not have a significant higher discrimination accuracy than just the regular risk factors like age, sex, and APOE4 in cognitively unimpaired individuals. But when we do combinations, then we increase the discrimination accuracy, and in particular for the younger people, the middle-aged people that are cognitively unimpaired, phosphorylated 231 and amyloid 40-40 had the higher area under the curves. Again, probably we should use different biomarkers, plasma biomarkers, depending on the population that we want to study, because in all the population, all these biomarkers behave very well. And phosphorylated 231 and 217 are the ones that have had the strongest association with amyloid PET retention. And I have shown you this longitudinal data showing that 231 and 217 are those biomarkers that are associated with longitudinal increases in amyloid PET uptake, and plasma phosphorylated 231 is associated with longitudinal cognitive decline in cognitively unimpaired individuals that are amyloid positive. So I would like to finish with that. Some challenges still with the blood biomarkers. We need more studies in the routine clinical practice. So I think that all people that are now listening to me, I think that we need to do something to start really measuring blood biomarkers in the real world. So more biomarkers to see how they work in our clinical practice. We have to study better these comorbidities, because we know that they have an effect, and again, more diverse populations. We need to figure out what is the role of blood biomarkers at clinical practice. It's a confirmatory test? I don't think so. I think that CSF is still, and it will always be, the confirmatory test. But we may use blood biomarkers as a pre-screening tool, or to choose better which patients should undergo lumbar puncture or amyloid PET. And where we should do the blood biomarker: in primary care, in secondary care, in research settings. So we need also more clinical utility studies to see also if blood biomarkers help us to change the clinical management. And the same questions for clinical trials. Do we need to use blood, or we will use blood biomarkers for confirmatory purposes? No, I think that in any clinical trial, we need to do CSF or amyloid PET to really confirm that it is amyloid. But maybe we can do before screening or pre-screening to be more efficient in the selection of the participants. I highly recommend to read this article that has been recently published about the Alzheimer Association recommendations of the appropriate use of blood biomarkers. I think that it's very sensible, and I think that well, something that we all need to read and of course discuss. So with that, I will finish. Thank you very much to all the people in Barcelona Beta, and especially my group of fluid biomarkers and translational neurology. Most of this data I've been presenting have been analyzed by Marta Milà, and the rest of the group, Paula, Federica, Armand, Margot, the people from the biomarkers facility led by Marta del Campo, Esther, Javi, the rest of the people from BBRC. Special thanks to the neurology department in Hospital del Mar, and especially to Albert Puig, who is leading the Biodegmar cohort, and all the team, the University of Gothenburg, Henrik Zetterberg, Kai Leno, and special thanks to Nick Ashton, with whom is always a pleasure to collaborate, and we are doing great things. And with that, I will finish. And just to say that we are recruiting people, both clinicians and researchers. So if anyone is interested, just let me know. Thank you very much.
Muchas gracias, Marc. Well, I really appreciate that you also share unpublished data, which is really excellent and enrich a lot the course. And it was really, really interesting. I have one question, one tricky question for you in the chat. If you were to start in a clinical setting, plasma biomarkers, which technique would you use, or in what technique would you invest?
All right, so
this is going to be recorded.
Right. Okay. Well, I mean, if the question is the technique, the answer is quite easy: an immunoassay, because I mean setting up a mass spec on these kind of techniques, although the biomarkers, the measurements are great in mass spec, but this is something that you cannot do in every center. So I would clearly say an immunoassay. Hi, Rik.
Hey, Marc.
So yeah, an immunoassay, that's for sure. Now there are many good, that's the good news, that we have not one, but really very good biomarkers from different platforms, and I can say, of course, some names from Simua platform, from MSD, from Fuji Review, and so on, and all of them really behave very well. Regarding the biomarkers, I already said that there are many that work very well, phospho-tau, also amyloid biomarkers, neurofilament as well, but neurofilament has a different meaning. It's not specific for Alzheimer's disease. Phospho-tau, I think that they are more feasible. Amyloid, some results, especially for the mass spec and also the immunoassays, are really, really good. However, for amyloid, especially with immunoassays, there is this issue of robustness that needs to, I believe, to be solved. But yeah, I think we have very, 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 not one, but many good techniques. So that's good news.
It's very good news indeed. I would like to ask you one quick question, because you position very strongly that you think that plasma biomarkers are not going to substitute CSF. I would like to give me an explanation. Why you think that? Because well, I mean, the results are fantastic. And of course, as you said, there are still some gaps that we need to fill in the knowledge of these biomarkers. But why you were so strong with your assessment?
I think that the evidence that CSF biomarkers are good for the diagnosis of Alzheimer's disease is so overwhelming that's very clear. And I also think that lumbar puncture and CSF is very, very, very safe. It's very cheap, and we can do a lot of measurements with CSF. So I think, and the evidence it's very clear. I think there's maybe a cultural thing that still now we are sometimes afraid of performing lumbar puncture, but I mean it's a very safe test. And to the diagnosis of Alzheimer's disease or neurological disease, it's a hard diagnosis. So we have to be very sure, and we have to do all needed. And the evidence for CSF is absolutely overwhelming. For plasma biomarkers, the results look very good, but we need to investigate more. I think that plasma biomarkers can be a substitution to CSF in those situations where there is a it's not indicated or contradiction to lumbar puncture, because there is anticoagulant drugs or whatever. And here the plasma biomarkers, of course, can substitute CSF. In very old people, maybe you don't want to do a lumbar puncture. But in the rest of the cases, I think that the result of introducing plasma biomarkers at the clinic should not be a decrease of lumbar punctures, but an increase of lumbar punctures. So we select better those patients that should undergo a lumbar puncture, so we increase the numbers of lumbar punctures. So to lose, I think that probably plasma biomarkers will be useful in order to rule out those patients that have a very, very, very low risk probability to have Alzheimer's disease. So those do not need to have a lumbar puncture, but the rest, they should go and do lumbar puncture. So probably we need to do it as a pre-screening and calculated cutoffs that have that are more sensitive than specific and with a high negative predictive value.
That was a very clear answer. And now we have to move to our next speaker. Thank you very much, Marc.
Thank you.
We have Rik Ossenkoppele. Rik is well, he's a big expert in the field of PET, especially in the application of PET in the clinic. I think it is where he has really he has also increased our knowledge in this field. He has a double position in not only one but two in two of the best centers of Alzheimer dementia in the world, in the Alzheimer Centrum in Amsterdam and also in Lund. And he's going to talk about PET amyloid and PET tau and PET in general in Alzheimer's disease. Thank you very much, Rik. The stage is yours.
Yeah, many thanks, Pascal, for the kind introduction. I think it can only go worse from here after this introduction. And thanks to both Pascal and Eloy for inviting me to talk today. All right, so today I know there's already a lot been discussed on Alzheimer's disease. So I'm gonna really restrict this to the relevant parts for the main part of this talk, which is going to be on both amyloid and on tau PET. And I understood from Pascal and Eloy that there is quite a bit of variety in expertise among the audience. So I'm going to approach this very broadly and hope there's something in it for everyone. But let's start with Alzheimer's disease and talk a little bit about tau and amyloid pathology. I guess the two things that are quite crucial for this talk is to understand that there are two things. So the first is that amyloid beta and tau pathology, they have a different temporal spatial onset. With that I mean that they change differently in terms of time. So in general, amyloid pathology, and especially in the neocortex, changes much earlier than tau pathology. And also you can see that they involve different brain regions. So whereas tau pathology is relatively focal, we can see that amyloid pathology early on relatively affects the entire neocortex. So that is one. The second, it's important to realize that Alzheimer's disease is characterized by a very long preclinical stage. So if you can see this and see this as a function of time, you can see that already in the preclinical stage of Alzheimer's disease, people have a lot of amyloid pathology already in the brain. And if you look at the entire time course, they spend actually most of their time into this preclinical stage where they have some biological signs of the disease, but no symptoms. So I think there have been a lot of developments in the field, and one is that we're now more and more moving towards a biological definition of the disease. So this is the ATN system, which you probably are all familiar with. And based on this ATN system, so amyloid, tau, neurodegeneration, then NIA research framework created a framework where this ATN profile is actually used to categorize individuals based on a biomarker profile. What you can see from here is that if individuals are amyloid positive and tau positive, regardless of their neurodegenerative status, it's called Alzheimer's disease. And only in the next step, the syndrome, so the clinical presentation is added to that. So again, if we look at people that are amyloid positive and tau positive, but they are cognitively unimpaired, this is called preclinical Alzheimer's disease, according to this criteria. For the MCI stage, it's called Alzheimer's disease with MCI or prodromal AD, and Alzheimer's disease with dementia at the dementia stage. So here it's really biology first, and then the symptoms are added. Then in 2021, another set of criteria was proposed by the International Working Group, and they explicitly state that the diagnosis of Alzheimer's disease should be restricted to people who have positive biomarkers together with specific Alzheimer's disease phenotypes. So in other words, we restrict this term to people that are symptomatic. So they have mild cognitive impairment or dementia of the Alzheimer's disease type, in addition to positive biomarkers. So here it's symptoms first, and the biology is actually secondary to that. So I'm very curious. So Zoom is for me very difficult, at least to make it interactive. But I would like the audience to put in the chat at this point whether they think that Alzheimer's disease should be defined based on the biology. So this would be more in line with the NIA criteria, or in terms of symptoms. And I'm coming back to this later in my talk, and it would be great to get some responses. People that would like to support either the biological view or the more symptomatic view. I'm curious what you think. All right, then, in terms of the second part where I'll discuss amyloid PET, it's good maybe to have a really quick word about PET in case you're not familiar with this technique. So with this technique, we inject a radio tracer that is slightly radioactive. The tracer travels through the bloodstream to the brain, and there it binds to a particular target. And in this case, it would be amyloid beta pathology. So at the moment that it binds in the brain towards this amyloid beta pathology, the signal annihilates and sends out a signal that enters the ring at 180 degrees. And based on the time it enters the camera, a back projection algorithm can be used to actually decompose a image based on that and get an actual PET image. So we see examples of that here. This is first an example of a autoradiography study where they looked at an individual that had normal cognition versus an individual that had symptomatic Alzheimer's disease. And if we look at the tracer binding here, we can see that there's actually no difference in the white matter. That's also what we expect. However, in the neocortex, there is a difference where there's actually no signal in the healthy control, but there is signal in the cortex of the individual with Alzheimer's disease. Then moving towards the living human brain, this is from the first publication based on this tracer called Pittsburgh Compound B. And what you can see here, based on the color bar, so where the hotter colors, so red and yellow, indicate greater tracer binding, we can see that there is substantial and widespread uptake of the tracer throughout the entire neocortex, which is significantly elevated compared to a control in an individual with Alzheimer's disease. So it's not always this straightforward based on diagnosis. We'll get to that, but generally the difference between a positive scan and a negative scan is as clear as we can see it here. So the radio tracer I mentioned before, again, is called Pittsburgh Compound B, so PIB. And in red, you can see that this tracer is labeled with the isotope carbon-11. And you can see that the half-life time of carbon-11 is only 20 minutes. So this means that you need to actually have a production site on campus, essentially, if you want to do a PET scan with carbon-11. Otherwise, the signal decays and you will not be able to get a high-quality PET scan. So this is, of course, suboptimal if you want to have a more widespread distribution of a PET tracer. So therefore, several amyloid tracers were developed that were labeled with a FAT. So, for example, florbetapir, flutamidamol, and florbetaben. And again, they are labeled with F18, which is a half-life time of 110 minutes. So it takes much more time for the signal to decay. And essentially, you can produce the tracer at one place and transfer it. So, for example, we produce it in Amsterdam and move it to Belgium and even the northern part of France. So this really increases the potential use in the clinic. And also these tracers were approved by the FDA and by the EMA for clinical use. And nowadays they are widely used actually in the clinic. So in 2015, so when these tracers were around for quite a while, we thought it would be time to do a meta-analysis to investigate the prevalence of amyloid beta positivity. So we wanted to know in the living population, how frequent is the prevalence of an abnormal amyloid PET scan? So as you can see, we did a thorough literature research. We approached the PIs of all the studies that have published on an amyloid PET tracer. And in the end, 55 centers worldwide contributed actually to this study. So we included about 8,600 individuals in this study. That included people with normal cognition, individuals with subjective cognitive impairment. So they have normal cognition, but they complain about their memory, but this is not objectified at formal neuropsychological testing. And there are individuals with MCI, so mild cognitive impairment. On the y-axis, you can see the rate of amyloid positivity ranging from 0 to 100. And here is the age in years. And what we can clearly see, regardless of the groups, is that the older people get, the higher the prevalence of amyloid beta positivity. And at age 80, you can see that in people with normal cognition, roughly 30% have an amyloid beta positive PET scan. So you will not observe this from the outside, but if you make a PET scan, you can clearly already visualize the pathology. Then as a next step, we added in another major risk factor for Alzheimer's disease. Actually, for sporadic Alzheimer's disease, this is the major genetic risk factor called ApoE, which comes in 3 different alleles. So the ApoE3 allele is neutral. E4 puts someone at risk for developing Alzheimer's disease. And the ApoE2 allele is protective. So now we're looking at the same plot as before, again, in people with normal cognition. And now we see that in individuals that are 80 and carry at least one ApoE4 allele, that the prevalence of amyloid positivity reaches up to 80%. So a really high proportion of people that are 80 and carry one A4 allele are amyloid beta positive. Another way of looking at this is if you look at the highest risk profile, so individuals with 2 copies of the E4 allele, you can see that the difference between the neutral line, E3, E3, is approximately 25 years. And if you carry at least one protective E2 allele, the difference is even 50 years. And you can see that there were very little people in the study who were homozygous for ApoE2. But actually none of them, even if you reach age 90, were amyloid positive. So this really shows that this allele is really protective, at least for the development of amyloid beta pathology. So then the next question is, okay, so if we don't can really measure an objective cognitive impairment, but we can measure all sorts of biological changes in the brain, what does this mean? And to answer that question, I really also always like to highlight this study because I think it's insightful and really nicely summarizes the extensive literature on this topic. So what they did in this study that uses ADNI data is they had a particular score. It's a very sensitive score for the earliest changes we can see in Alzheimer's disease. It's called the preclinical Alzheimer cognitive composite, or the PAC. And the more negative the score, the worse the performance on this test. These are the years after the baseline amyloid PET scan was performed, and there were 2 different groups. In blue, you can see people with normal amyloid, and in orange, people with elevated levels of amyloid pathology. What you can actually observe is that for the first couple of years, there's actually no difference between those 2 slopes. We can see that only after quite some time, let's say 4 years, that those slopes start to diverge. So again, cross-sectionally, there is a biological thing observable using PET, but that's not measurable, at least with the PAC. It takes actually quite some time before this risk actually manifests. So what is a potential mechanism for this? And this is a study that uses the familial forms of Alzheimer's disease as a disease model. It's an appealing model because based on the onset actually of the parents, you can get a very accurate estimated year of onset in the individual, which should be more or less the same as the parent. So in this case, let's say that the father or the mother of an individual here developed the disease at age 50. If you would develop this individual at the age of 25, so 25 years prior to onset, this is what we get. And they grouped all the individuals based on their estimated years of onset. They did imaging using 3 different modalities. So they used amyloid PET, they looked at glucose hypometabolism using FTG PET, and they looked at cortical thickness. What we can see, if we look 25 years before the estimated age of onset, there's already an increase in amyloid beta pathology in the brain, which increases to about 15 years before. But then once you approach sort of the age of onset, you can see it's relatively stable. So the brain is already sort of saturated, has reached a plateau. And then actually there is widespread amyloid beta pathology in the brain. What we see for FDG PET is actually quite interesting. So you would, of course, expect a decrease of glucose metabolism over time. This is actually what we see when we get closer to the disease onset. But at the initial stage, or when amyloid beta pathology starts to occur, we actually see an increase in FDG PET. So we actually see hypermetabolism. So there are a few potential explanations proposed in the literature. One is that maybe this presents a compensatory mechanism. So the brain is trying to deal with the toxic effects of amyloid beta pathology. Another explanation is actually that the increased neural activity may actually be a mechanism through which amyloid beta deposits in the brain, or through which it spreads the pathology throughout the neocortex. For cortical thickness, we see a very gradual increase of cortical thinning over time, especially highlighting the medial temporal lobe and all sorts of Alzheimer's disease specific regions. But there's one thing that's quite striking. If we look at the relationships between amyloid beta pathology and then the downstream effects in terms of atrophy and glucose metabolism, and they're really apparent in two different regions. So one is the medial temporal lobe. That is a region that's highly vulnerable for neurodegeneration, so increased atrophy and increased hypometabolism. But this is also a region where at least fibrillar amyloid beta pathology, which we measure with PET, is relatively low. So there's a bit of a mismatch here. And there's also a mismatch, but then in the other direction, in the frontal cortex, especially in the medial prefrontal cortex and also here in the lateral prefrontal cortex, where there's a lot of amyloid beta pathology already early on in the disease. But there the levels of brain atrophy and glucose hypometabolism are relatively modest. So keep this in mind for the second part of this presentation. So to conclude on this part, H and ApoE4 are important risk factors for amyloid beta positivity. Amyloid beta positivity is associated with longitudinal cognitive decline. And again, it's very hard to dissect the cross-sectional effects. And it seems based on the model that A beta becomes abnormal before we see apparent brain atrophy and hypometabolism. But there's also this temporal spatial disconnect between amyloid beta and neurodegeneration. I'm not sure if we take questions in the middle of the talk or whether we wait for the end of the presentation. I'm open for both.
We wait for the end.
We wait. Perfect. Action. Then I'll continue with the part on tau PET, where I'll spend actually most of my time because I think it's also the most recent and perhaps also the most relevant developments have been going on in this field. I guess Marc has probably talked about plasma p-tau a lot already, but still probably important to consider why we would want to study tau, and especially why would we want to study tau using tau PET. So first of all, abnormal tau correlates very strongly with the severity of the disease and with progression of symptoms. It is linked to function and degeneration of neurons. But most of what we knew about tau until very recently came from animal or cell culture studies, from postmortem neuropathology, or from CSF measures. And of course, they're all very unique and elegant techniques, but they also have some inherent disadvantages. And especially we contrast that against neuroimaging with PET. So first of all, I think we are measuring with PET tau pathology in a species that we eventually want to cure, so in humans. So there is a lot of ecological validity with respect to PET relative to animal models, for example. Then we can also study early disease stages, which is often difficult in neuropathological studies where people present at brain banks at very advanced stages of the disease. We can also do longitudinal measurements, so take multiple measurements over time. And I think the biggest discriminatory power of PET relative to the biofluid markers, so CSF and plasma, is that we get a very detailed mapping of the entire brain. So we do one brain scan and we can assess essentially every part of the brain that we would be interested in. And especially for tau, this is a major advantage rather than just get one number representing p-tau levels across the entire brain. So for tau PET, it took a little bit more time actually before the tau PET tracers came to the market relative to amyloid PET, and it has to do with the fact that tau pathology is a little bit more difficult to track. Main reason is that, of course, the PET tracer needs to pass the blood-brain barrier, which is already a big challenge. But in the case of tau PET, which is an intracellular protein deposition, it also needs to cross the cell membrane. So it's a double challenge. But in the end, it seemed to work very well. This is, for example, one example with F18 for tau pair. And to show that it's specific to tau pathology and not to amyloid beta pathology, this study was performed where in this tissue of an individual with amyloid that was amyloid beta positive but tau negative, there's essentially no binding of the tracer. Whereas if we look at someone that is both amyloid positive and tau positive, there's actually signal. So we see clearly throughout the neocortical layers binding of the tracer. So suggesting it specifically binds to neurofibrillary tau pathology. And something very similar was found in an antemortem versus postmortem comparison of an individual that underwent both tau PET and amyloid PET during life, passed away relatively shortly after the PET scans. So the tau PET values during life could be compared against the 88 positive staining post-mortem. And for tau PET, you can see a very clear correlation, very high across brain regions in this individual. And this relationship was completely absent for amyloid beta PET. So again, suggesting the tau PET is related to the post-mortem neurofibrillary tangle tau burden. So same as for amyloid PET, we now have multiple tracers at our disposal. And I'm just listing here a few of them. There are even more, but I think these are currently the most widely used. So this is fluortaucipir, which is so far the most widely used. It's also the only one FDA approved tau PET tracer. We have MK6240, we have RO948, and we have PI2620. But I guess what's really, what they all have in common is that they distinguish very strongly between people that are cognitively unimpaired and people that are cognitively impaired. You can clearly see this from the brain images, and also that the patterns are quite similar across the different groups. So for example, actually all of them show high tau load, or at least tau PET tracer binding in the lateral temporal parietal cortex, in the medial parietal cortex, including the posterior cingulate and the precuneus, and also in the medial temporal regions, as well as the inferior temporal cortex. So here I had to be very selective. There is a lot of research, of course, on tau PET. I picked two topics. The first one is on atypical variants of Alzheimer's disease, and the other one is on modifiers of tau progression using PET. So for the first one, I'm coming back actually to the previous presentation. Sorry, one of the previous slides I showed, where we talked about this disconnect between regions that have amyloid versus neurodegeneration, sometimes high versus low, or the other way around. So in general, this is what an amyloid PET scan looks like if it's positive, and that's regardless of the clinical phenotype. So there's very widespread amyloid pathology, normally spares the sensory motor cortex, but otherwise occupies most parts of the brain. So we were wondering whether tau could be the missing link, connecting sort of the regional neurodegeneration. And the first tau PET scan I saw in a living human was in this individual that had posterior cortical atrophy. It was during my time as a postdoc at UCF in San Francisco. And we studied this individual with posterior cortical atrophy, or in other words, the visual variant of Alzheimer's disease. So this is an atypical presentation where at least 3 of those features listed here are present in early stages and also predominantly, with sparing of memory, language, and executive functions. And symptoms you can think about are, for example, space perception, or if you overlay 2 objects at the same time, they can only identify one. Difficulties with perceiving objects, there's left-right disorientation, there's a whole bunch of symptoms. And they all relate to processing of visual information. So we did 4 imaging modalities in this case. And if we look at the FDG PET scan, so we look at the hypometabolism, the red areas indicate regions that are hypometabolic. So they're suggestive that those parts of the brain are less active than they should be. And in line with the clinical presentations, those regions are really highlighting those posterior areas that are responsible for visual processing. We also did an amyloid PET scan, and here you can see that both the posterior and the anterior parts of the brain are involved, as we also saw before. So then the big question is, how will this tau PET scan look like? And what we found is that the tau PET scan, here red areas indicate areas where there's more tau pathology in the brain. And you can see if you overlay the tau PET scan on the FDG PET scan, they're almost a mirror image, like 2 parts of the same puzzle. So in other words, areas where there's like a high tau load, for example here, you can see that those regions tend to show fierce hypometabolism. You can also see the overlay here. And it's also the other way around. So regions where there's relatively little tau, we can see a normal level of FDG PET uptake there. So this was just one case. So we repeated this experiment, but now in 10 individuals. So you're looking at here at group maps of amyloid PET using PIP and tau PET using fluorotaucipir. And we see the very same thing. So there's amyloid pathology all over the brain, including both the posterior parts of the brain and the anterior parts of the brain. Whereas for tau PET, the signal is really restricted to those posterior areas of the brain. And if we link that to what we know about the basic neuroscience information on visual processing of the brain, we can see it really nicely overlays the visual system, right? Where there is a ventral stream that is heavily involved in identifying objects, for example, or faces or text. And there's also the where stream going up into the parietal cortex. And you can see that the tau PET pattern beautifully overlaps with this visual system. So this may explain the clinical manifestation of those individuals. So we also see this in other clinical variants of Alzheimer's disease. So for example, in language AD, we see that there's much more tau pathology in the left hemisphere compared to the right hemisphere. And we know that language in most people is dominant in the left hemisphere. So for memory, we see a lot of tau pathology in medial temporal lobe structures, which we know are key for memory function. And also in motor AD, we see quite uniquely uptake in central motor areas, which we don't see in any of the other variants. So there it seems to be very specific. There's one exception, that's for behavioral AD, where based on the symptomatology, you would maybe expect a bit more of the frontal involvement. We don't really see that, so that's still a mystery. So if you want to learn more about this, you can look up our previous publications on this. Second part is, so actually based on previous studies, we knew that if you look between individuals, that there is a certain staging mechanism of tau, which is suggesting that there is actually spreading of tau pathology. We have also seen this, of course, in animal models. But I guess tau PET is really the only way to objectively show in individuals during life that tau pathology progresses over time. So this is the first longitudinal study out there in the literature. And what it shows is here, as a function of age, the tau PET SUVR over time. So this data point, those data points belong to the same person. You can see a clear increase over time in the orange data points. Those are individuals that have symptomatic Alzheimer's disease. So they either have MCI or AD dementia. But you can also already see in people that are dark blue, so they are amyloid beta positive individuals, that there is a slight increase if you look at this. If you put this into numbers, there's a roughly 3% annual change in tau accumulation for the impaired individuals, and there's roughly 0.5% for the amyloid beta positive controls. They are the ones in blue. And those rates vary a little bit across studies, and they sometimes go up to 10%. It depends a little bit on the study and also on the methodology. But the key message is that we can actually monitor changes in tau pathology in the living human brain using tau PET. So then, of course, it's important to understand what is driving these changes in tau pathology, right? So we already know that tau is so closely linked to neuronal function, neuronal health, and also cognition, that we really need to understand how tau behaves in the living human brain. So one of those modifiers of tau progression is amyloid beta pathology. So what is the evidence so far? So first of all, tau PET positivity is almost exclusively seen in people that are also amyloid positive. So for example, if you look here at the right part of this quadrant, those are the people that are tau PET positive. You can see that roughly half of this total sample was amyloid beta positive and tau PET positive. And that was a very small proportion of amyloid negative people that were tau positive. We do see the other way around a bit more often. So amyloid beta positive, but tau negative first, suggests that it's really amyloid beta pathology becoming abnormal first, followed by abnormalities in tau pathology, at least when measured using PET. So this is a complicated figure, but the message of this paper is quite straightforward. And that is that they did find a relationship between change in amyloid beta pathology over time. You can see that here. As a mediator of change in tau pathology over time. So again, those deltas of both are associated. And finally, what we also see is that in the absence of amyloid beta pathology in the brain, tau pathology is really restricted to particular areas of the brain, especially what we see in PAR, so primary age-related tauopathy, so mainly in limbic areas, but the wider parts of the neocortex are relatively spared. And you can see here in the lighter color that only if there's a beta pathology present in the brain, we see spread into those regions. So it really seems that if you are seeing widespread tau pathology, that seems to be almost exclusively the case in individuals that are also amyloid beta positive. A second important modifier is age. And this may actually be in a direction that may not be fully intuitive in the first place, but we should remember that we're here looking at people that are symptomatic and are also amyloid beta positive. So to start with, we did a study where we looked at the difference between early onset AD and late onset AD. And what we found is that actually the early onset AD cases had more tau pathology than the late onset AD cases throughout the neocortex. And we see this actually across study. This is a very robust finding. And also here you can see that actually the younger the individuals are, the more tau pathology they have. So there's this inverse correlation with age, at least in amyloid beta positive individuals with symptomatic Alzheimer's disease. And we also see this over time. So this is a study where you see age. This is a slope in tau PET over time. And in people that are amyloid beta positive, you can see that the younger cases tend to accumulate more tau every year than individuals that are older. There also seems to be a sex-specific effects where female individuals show higher baseline tau PET levels. And in this case, the study by Rachel Buckley was showing this relative to the amount of amyloid pathology in the brain. So here we can see the slope for male individuals. So across all cases, more amyloid is related to more tau pathology. But this is exacerbated in female individuals, where at the same level of amyloid pathology, they exhibit higher levels of tau load in the brain. We found more recently that females tend to be more resilient to tau pathology, so they have higher brain resilience. So they're preserving their cortical thickness better relative to males in the face of similar levels of tau pathology. And the finding of accumulating faster tau pathology over time was also found here in females, especially in amyloid beta positive females, where you can see that the rates of change are higher compared to males. And the final one I would like to discuss today is the concept of connectivity. There's a lot of literature, basic science literature on this, that tau may be spreading through the brain across potentially connected neurons. There have been many, many studies on this. I just highlighted some of them here. This is a study we did a while ago, where we looked at a group of individuals where we made a tau PET covariance map. So we put a seed into the occipital cortex. We looked at how that covariated across the rest of the neocortex. And we did the same thing for functional connectivity, where we used the same seed and then looked how well that particular seed was connected to the rest of the brain. And if you make those two maps and look at the functional connectivity map versus the covariance map, you can see that they are very much alike. So they're very similar. And also, if we just quantify this across all the voxels in the brain, so here looking at the fMRI measure, and here look at the tau PET covariance t-score, you can see a very strong correlation here. So this would support the notion that tau pathology spreads through circumscribed brain networks. But again, remember, this is just a cross-sectional study. So we did a similar thing looking at the longitudinal design. So now you're looking at the y-axis, looking at a change in tau PET. And again, what we see is the stronger the connectivity at baseline, the more likely that region is to accumulate more tau pathology over time. So in other words, the functional brain architecture is also associated with the rate of tau accumulation. So to summarize the research part on tau PET, we can actually capture progression of tau using PET with an annual range between 0 and 3% for healthy, cognitively unimpaired people, and between 3 and 10% for people with MCI and AD dementia. And we also have identified several modifiers that can actually impact the tau progression rates as measured by PET. So to end this talk, I would like to talk a little bit about the potential clinical applications of tau PET, because it really feels we're sort of on the verge between tau PET as just a research tool and it being more widely applied in the clinics, of course, very selectively. So this is maybe a first attempt to see whether tau PET could be a potential tool for the differential diagnosis of AD dementia versus non-AD. So here we're looking at group average maps of tau PET in healthy controls, where we can see there's very little tau PET signal, which slightly increases at the MCI stage. So these are all amyloid beta positive individuals with MCI. You can see that in some specific AD regions, including the medial temporal lobe and the inferior temporal cortex, there are already elevations of tau PET signal. And this further extends into other AD-specific areas at the dementia stage. So here we grouped all the non-AD disorders together, and as a whole, we can see that there is very little tau pathology over time. So this tau PET tracer really seems to be specific to the tau species we see in Alzheimer's disease, and less so for non-AD. And I should mention this is a study done with fluortaucipir. So then, as a next step, we quantified the amount of tau pathology in a temporal region of interest. The dotted line here indicates the threshold. So if you're below this threshold, your tau PET scan is supposedly negative. And if it's above it, the tau PET scan is positive. And in a group of people that were with AD dementia, you can see that the vast majority is way above this tau PET positivity threshold. So the same is actually true for prodromal AD, although you can see that the total tau load is already lower, and there's also a lower proportion of people that is amyloid positive. But if we look at all the other groups, so we're talking about the controls, we're talking about a variety of other neurodegenerative diseases, including Lewy body, PSP, vascular dementia, etc. The majority of them are actually tau PET negative. There are a few exceptions. For example, a semantic variant of PPA that shows a tau PET positive signal, and also some people with Lewy body dementia. But for the other diseases, it's mainly a negative scan. So if you look at some diagnostic properties, you can see there's a very high area under the curve for distinguishing AD dementia from these non-AD dementias grouped together. And also the sensitivity and specificity is rather high. But then, of course, the next question is it better than the more established markers we typically use in the clinic? So we contrasted the performance of tau PET in 3 regions of interest against 3 widely used MR measures. So this is, for example, cortical thickness in AD-specific areas. We have MRI measuring cortical thickness across the whole brain. And this is specifically looking into hippocampal volumes. And if we look at the area under the curve, again, for distinguishing AD dementia versus non-AD neurodegenerative disorders, you can see that there's actually a big difference between the tau PET regions of interest and the MR measures. So at the dementia stage, tau PET clearly outperformed these established MR markers of AD. This outperformance is actually still true at the MCI stage compared to non-AD. However, you can see that the area under the curve is much lower at the MCI stage compared to the dementia stage. So in other words, the diagnostic performance of tau PET really seems to drop at the MCI stage of AD. So the approval of FDA for fluortaucipir is also really limited to people that are at the dementia stage and are suspected for Alzheimer's disease pathology, again, at the dementia stage, among others based on these data. I guess, of course, having a correct and accurate diagnosis and timely diagnosis is highly important. One of the next questions that patients always ask our clinicians is, first of all, is there anything we can do? And the next one is, what can we expect? So prognostic information is highly valuable for clinical use. So we investigated this in multiple different ways. This is a cross-sectional study where we try to link the tau PET levels, as well as amyloid levels, as well as cortical thickness, with a variety of cognitive tests in preclinical Alzheimer's disease. So this is Alzheimer's disease defined as being amyloid beta positive, but having still normal cognition. And what we can see is, if we look at those correlation between tau PET and the other markers in a variety of brain regions, we can only see significant associations for tau PET and not for any of the other modalities, suggesting that tau PET, even at this stage, can already detect some subtle changes in cognition. If we look at symptomatic Alzheimer's disease, so now in red, I'm only showing the FDR corrected areas, so the ones that are surviving multiple comparisons. We can see significant associations both for tau PET and for cortical thickness. We should mention that the beta coefficients in general are higher for tau PET, and also we see these associations across more regions and across more domains than MR. So the next step, of course, was to test whether we could also predict future cognitive decline. So that's what we did here. On the y-axis, you can see the slopes, the annual change in MMSE, so a global test of cognition. And on the x-axis, you can see the tau load in the top panels and the cortical thickness in an AD-specific region. And if we just compare the amount of explained variance or the effect sizes, you can see that both across the whole group, in amyloid beta positive MCI and in A beta positive cognitive unimpaired people, tau PET is a way stronger predictor of cognitive decline over time compared to MRI, already in those earliest stages of the disease. So then we brought this actually to, I think, to the next level, where we did a multi-center study where we included people that were cognitively unimpaired, had baseline amyloid and tau PET scans available, and had at least 2 cognitive or clinical time points available. So this study includes roughly 1,300 people from 7 different cohorts, and we grouped them based on their amyloid and T status, and again defined by PET. So we have amyloid negative and tau negative, we have amyloid positive and tau negative, we have amyloid positive and tau positive, but only in the medial temporal lobes, MTL, and we have amyloid positive and tau in the neocortex, so tau NEO positive. And when we look at progression to mild cognitive impairment as a function of their AT grouping, we can see that both the amyloid positive and the tau PET positive groups are at very high risk of future cognitive progression to mild cognitive impairment. If you look at the hazard ratios, for example, compared to the complete negative group, it goes up to 19 in the group that has amyloid and tau in the neocortex. And this hazard ratio is even higher when we look at progression to all-cause dementia, where the hazard ratio reaches up to 41 in cases that are amyloid positive and also positive for tau in the neocortex. You can see it here. So I would like to get your opinion whether maybe some of you have changed their mind based on this. But to conclude this talk and then have a little bit of discussion on this, I hope I've shown that tau PET retention corresponds to neuropathological findings. That tau, but not amyloid beta PET, the patterns mirror the sites of neurodegeneration. Tau pathology may drive cognitive loss, but also distinct variants of Alzheimer's disease. Meaningful changes in tau pathology over time can be tracked using PET. We also know that tau pathology has now been approved for FDA, at least one tau PET tracer for diagnostic use at the dementia stage. And I think tau PET has great potential for prognostic use in early stage AD. We're not there yet, but we're about to get there. So I think I'll stop here. I'll also stop sharing my slides, and I look forward to discuss some of this with you.
Thank you very much, Rik, for this beautiful presentation. I think we have one question in the chat. By the way, everyone say biology, as you can see. That was anonymous.
Obviously, I hadn't time to read it during the talk, but
yeah.
I see there's a lot of agreement here on the biology. I also see that a lot of people didn't vote.
Yeah.
So, yeah.
See, I think there is a question. Yeah, someone is asking what do you think would be the role of PET and specifically PET tau, I think, in the future scenario of disease-modifying treatment? Having heard the advances in plasma biomarkers and what CSF biomarkers is offering already, what do you think would be the role of PET?
Yeah, great question, and I think very relevant. So I think one potentially important one is participant selection. And this can actually be the case not only for anti-tau trials, where it of course makes sense to include people that actually have tau pathology in the brain, right? So that we can target the actual pathology. But for example, in the donanemab trial, they selected individuals that had sort of mild tau pathology. So they excluded people with too little tau pathology in the brain, but also excluded people with too much tau pathology in the brain, with the idea that by removing amyloid from the brain, we're trying to reduce the direct effects of amyloid beta pathology on cognition, but probably maybe the biggest sort of disease modifying part is through removing tau pathology in the brain. So just by including people that actually have mild levels of tau pathology in the brain, these anti-A beta treatments can potentially be more effective. Clearly, in anti-tau trials, you also want to include people that actually have tau pathology. And I also think tau PET is probably a more robust measure for monitoring change over time during treatment or during clinical trials, to see whether we have successfully removed tau pathology from the brain. I think tau PET is crucial. I'm pretty sure that Marc has shown you also that the plasma, for example, the plasma p-tau biomarkers, they relate to tangle pathology, but also very strongly to amyloid pathology. So if we do see a reduction in plasma p-tau, we are not certain that the drug actually effectively removed tau pathology from the brain. Maybe the drop in plasma may be due to the removal of amyloid beta pathology from the brain. So I think for tau PET, we are more specific to nerve fibrillary tangle pathology.
Great. And also related to this question, do you know what is how is the process of approval in Europe of tau PET? In which stage is this?
Yeah, it's a good question. So actually in Amsterdam, we are about to start a clinical value study of tau PET, and we're going to use flutalzapine for doing that. And my thinking is that probably the company would be very interested in those data to support their potential approval to the EMA. As far as I'm concerned, they haven't submitted like an application yet in Europe, and also as far as I'm concerned, none of the other tau PET tracers has submitted any approval yet in Europe. So I would say at this time there's no EMA approved tau PET tracer available. But yeah, again, clinical value studies are ongoing or are about to start.
Yeah, and I think the fact that we may have available next year treatments, it will boost this the application process, and they will be more inclined to do it. Yeah. Well, I'm so puzzled about what you say about the frontal variant. That what is your hypothesis of that? I didn't know that it's not correlated with tau pathology. What's happening in those patients?
Yeah, that is actually a question that keeps me like wondering for a long time already. I don't know if you have a saying in Spanish that is something like there are multiple ways to Rome. Is there? Yeah. And I think that saying really applies to the behavioral variant of Alzheimer's disease. So we have a behavioral phenotype. So we see very early on, and we see very prominently changes in behavior and personality. But in those patients, we haven't been able to identify a clear biological signature. So we have tried really hard. So we looked at tau PET, we have looked at MRI, we have looked at FDG PET. We have looked at subcortical volumes. We have done network analyses. We have even looked at post-mortem tissue, where we looked at von Economo neurons. Those are very specific neurons, very important for our social functioning. And we haven't been able to identify any biological links that could clearly explain this phenotype. So my guess is it's probably a mix. Maybe in one individual, extensive white matter pathology could be causing the behavioral symptoms. In others, it may be their premorbid personality, right? So they have a personality that makes them more prone to developing behavioral symptoms. And then it doesn't really matter where amyloid beta pathology and tau hit the brain. And yeah, so it's probably like a mix of reasons why people arrive at that phenotype.
So maybe it's a very heterogeneous clinical category, right?
I'm afraid so. Yeah. And it's clearly different also than for example PCA and logopenic variant PPA, right? Where we also in clinical criteria we use that anatomical information to support the diagnosis. When we proposed research criteria for behavioral variant AD, we did not include MRI or FTG as sort of features. Because they're not correlated with the outcome.
Yep. I think we have another question. He said he chose biology in the question you asked, but need to take into account the individual difference, explaining this connection between these and clinical symptoms. You touched the modifiers of tau deposition. Are lifestyle factors relevant?
Yeah, thank you for this question. And when looking at our data, I think two things are very apparent. So I think if we look at those survival curves, you can see that, of course, those amyloid and tau positive individuals are at really high risk for future cognitive decline. But you've probably also noticed that not all of them did decline, right? So that there are highly resilient individuals in there. Some of them, even after 7 years, were still cognitively unimpaired. And also some were, even if you measure them neuropsychologically, they were quite stable over time. So apparently there are some people that can deal with neocortical amyloid and tau pathology. And that group is relatively small, so we haven't been able to dive deeper into that. But this group, to me, may actually prove very important towards really finding on what can certain individuals protect against clinical Alzheimer's disease. So they have an abundance of pathology in the brain, but still they're cognitively normal for quite an extended period of time. So very important and interesting group to study. But again, it's a small sample and they come from 7 different cohorts. So with the available data set, that will be very difficult. So we need to collect a little bit more data to dive into that. And of course, lifestyle is a potential explanatory variable. But I would, for example, also be very interested to look at maybe at certain CSF proteins associated with neuroinflammation or synaptic activity. Maybe there are certain genetic variants, right, that protect people. So both lifestyle factors and biological factors will be very important to study those. Yeah.
I want to ask you another question about the other tauopathies, in addition to Alzheimer's disease. How far are we to be able to be helpful in the clinic using these methods?
Excellent question again. So I've showed you 4 tracers now. So I would say that for flutalzapir, MK, and R0948, it's pretty clear that there's not sufficient signal to, for example, primary 4R tauopathies, right? Like CBD or PSP or like Pick's disease. We don't see that. That may be different for the other one, PI 2620. So there are a few studies now that actually showing that at least at a group level, there's quite a strong discriminative accuracy between 4R tauopathies and essentially healthy controls. But your question really was about the clinical application, right? Which means that we need to apply it at an individual level. And I personally don't think we are there yet. I saw in my so I get an email update every week of new papers, and I saw actually a new paper coming in from a group in Japan that looked actually at the clinical value of tau PET, and I think they use PI in, among others, 4R primary tauopathies, and they did suggest that they did change, for example, the diagnosis and treatment. But I haven't read the full article yet, but the abstract seemed promising. So I may well have to send you that paper, and I also have to read it myself first. Yeah.
Great. And okay, I think I have one last question about any other tracer. If you are aware of the developing for other diseases, like, for example, alpha-synuclein or I don't know, microglia and inflammation.
Yeah.
What do you think about also this line and the future of how can this help us in the clinic?
Yeah, excellent question. I think for alpha-synuclein, that looks a bit promising, I would say. So in the last year, there have been some results presented on an alpha-synuclein PET tracer. It did show an increased signal in MSA, for example, in multiple system atrophy, slightly elevated signal also in Parkinson's disease, but not a big difference actually in for example, Lewy body dementia. So it seems to be in people with very concentrated alpha-synucleinopathy that the tracer might work very well. For DLB, not yet, but I guess the fact that we are able to measure it, at least in those clinical syndromes, that's promising. And yeah, in my experience, once tracers start to emerge, that are tapping into that, it doesn't take very long for others to follow. We have seen this exact same thing for amyloid and tau. So apparently many people are working on it, and at some point it all comes together. So I'm hopeful for that. I would be very interested in seeing a TDP-43 tracer, which I think is missing a lot, right? Also, there are no good CSF or plasma biomarkers or any other markers to identify TDP-43 pathology very well. And also for the primary 4R tauopathies, maybe PI works. There is another tracer, PBB3, which is now sort of developed and has potential to measure 4R tauopathies and maybe PIX disease as well. So there are some developments there. Neuroinflammation. So my honest answer is that I've been looking for years now to start incorporating a neuroinflammation PET tracer into my own studies. But so far I haven't been convinced yet. There's always something with them. So either there's a specific genotype that makes some individuals like high affinity binders, irrespective of their true neuroinflammatory state, they show a very high signal. Or the signal to noise ratio is very poor. So far I haven't been convinced yet, but I keep my eyes wide open because if you just look at the genetic evidence, there needs to be something there. So once there's a tracer that I personally think is good enough, I will not hesitate to use it in my studies.
Thank you very much for the excellent talk and the very interesting discussion. I would like to congratulate all the speakers for the excellent presentation. And muchas gracias a todos vosotros que estáis ahí detrás una vez más. Yo creo que ha sido un día fantástico, hemos aprendido muchísimo y bueno, nada, que tengáis una buena tarde y nos vemos mañana.
Muchas gracias. Adiós.
Bye, bye.